no magnetic field or loss of what we call residual magnetic field in the field coils, okay? Because we're talking what's called a self-excited generator. And if we don't have any small amount of magnetism left in these field coils, we can't build up, okay, any voltage, can't create any voltage. So that's what failure to excite is. We're not creating any voltage, and that's caused by a loss of residual magnetism. The next one is voltage fails to build up, and that's caused by the pilots, okay? It's usually caused by the pilots in a DC generating system starting the engine, starting the generator with the generator switched on. It will never build up enough excitation voltage to produce a big output, okay? So we're expecting 28 volts, we might only get 10. It's no good. And what the problem is the pilot has started the engine, started the generator with the generator switch on. So what we use the term is, it must be run up offline. So the generator must be run up with the generator switched off. Reverse polarity. Okay, there's only two ways that can happen. It's been connected inside wrong, causing the magnetic field to be the wrong way. Or, here's the biggest one, the biggest problem for this. A DC generator has two leads, a positive and a negative. If you get them round the wrong way, you can get reverse polarity, okay? Insufficient voltage, okay? Insufficient voltage is usually caused by some sort of high resistance, okay? The voltage getting dropped, like dirty commutator, worn or dirty brushes. Another thing is what we call a glazed commutator, got very, very high resistance. Or the other one, it also causes insufficient voltage, is not rotating fast enough, okay? This one here, excessive voltage, it's rotating too fast, okay? It's rotating too fast. And sparking is caused by a dirty commutator or a glazed commutator. So those are the basic faults, okay? Those are the 6 basic faults and what causes them. Now, we said what causes voltage is magnetic field, number of coils, and the speed of rotation, okay? Let's look at how we can change the voltage, or better said, how I can keep the voltage at the correct level, okay? Let's look at this. I've got a generator, the number of coils. Can I change the number of conductors in the armature? No, because they've been built. Can I control the speed of rotation? Well, it all depends. If I need the engine to go fully forward, okay, put the throttles fully forward, the RPM of the engine would go up, the speed of the armature would go up, and my voltage would go up. If it started to descend, I put the throttles back, the speed of the engine would slow down. So in reality I don't have much control over the speed of rotation of the armature. But what we can do is we can control the strength of the magnetic field. Okay, low rotation, high magnetic field. High rotation, we lower the magnetic field. So now we're not going to use permanent magnets, we're going to use an electromagnet. So how do we control the voltage output of a DC generator, and it also applies to an AC generator, we control the strength of the magnetic field. So we control the strength of the excitation. Excitation field, okay? So that's the magnetic field, is also known as the excitation field. So we control the strength, increase it if the voltage is too low, and decrease it if it's too high. Now, my DC system, all my DC systems on my aircraft operate at 28 volts. So I need my output of my voltage of my generator to be a constant 28 volts. Okay, but as already said, this will be a problem with the speed, changing the speed of the engine. Okay, this will be a problem when you change the speed of the engine. So what we're going to do is change the strength of the magnetic field. Okay, all we're going to do is change the strength of the magnetic field, and this is what we call voltage regulation. Voltage regulation, we are going to control the excitation of our generator. Now, there's two types of voltage regulator out there. There's an electronic one, gentlemen, that controls the excitation electronically. And there's what's called an electromechanical device, which is still used in some turboprops. Okay, it's still used in some turboprops. We all like electronics, don't we? Okay, we all like electronics. No? Anyone like electronics? No. So we're going to look at an electromechanical device, and it gives us an understanding of how we get my output voltage. And then we'll have a little look at an electronic voltage regulator. Because one of the things we're required to you're required to understand is some basic faults, okay, in voltage regulation. So we're going to look at the appropriate voltage faults in this electromechanical device. Here we go. One on the right. Okay, one on the right. That is an electronic one. This one on the left, okay, is called an electromechanical device. It's also known as a carbon pile regulator. And what we've got in here this bit here is actually discs of conductive carbon. And down here, you can see this big coil here. This is a big electromagnet. Okay. And on this base unit here, there's a base unit here. That's made of some sort of magnetic metal. Okay. So some ferrous metal. That's how it looks. Okay. It is quite heavy. Okay. They are quite heavy. But again, they're still used in some turboprops. Still use this sort of device. So let's have a look at a block diagram of this carbon pile regulator. There's the first thing here. We've got the carbon pile itself. Yep. And we've got discs of carbon. We're going to look at the discs in a minute. We'll get discs of carbon. And they're pushed up, okay, by this leaf spring, okay? It's pushing the carbon disc together. Down here, we have what's called a voltage coil. It's going to produce a magnetic field that's going to try and pull the base of this carbon pile down. And what it's trying to do is separate these carbon discs. We'll come back to that. So I'm going to have a quick look at these carbon discs. Here's a little diagram of what a carbon disc looks. This is what it would look like under a microscope. So we're not talking big movements. The carbon discs, as you've seen there, they look grey, but they look flat. But if I put them under a microscope, they look like they've got lots of you can see they've got a lot of ridges. It's quite rough. And if I put right now, let's say I put a DC supply, have I got a current flowing right now? Anyone? No, because they're not touching. And it's conductive carbon, but they're not touching. Let's see now I push them slightly together. And let's say this point and this point touch. Have I now got a complete circuit? Yes, I have. Okay. So my cross-sectional area, okay, if we look up here, my cross-sectional area is small. That means my resistance must be high. If we now look at the voltage dropped across these two carbon discs, I've got a high resistance, therefore the voltage drop must also be high. And if I have my excitation coil there, I'll have a very low, so if I put 28 volts there, I might drop, let's say, 14 volts. That only leaves 14 to produce an excitation field. I now push it together further, okay? And I really push them together, so basically all these bits are touching. My cross-sectional area, the area of the disc that is touching is, let's call it high, okay, or large. My resistance is smaller. My voltage drop is less. Okay, and let's say now we have 20 volts getting across that carbon pile, which now means I've got, okay, sorry, I've got 4 volts, sorry, smaller resistance. I've dropped less voltage, I've only dropped 4 volts, which basically means I now have at my excitation field 20 and my voltage goes up. So this is the principle here. This spring is going to, leaf spring is going to push the discs together, increasing the cross-sectional area. If I increase the cross-sectional area they're touching, I have a lower resistance. That means I'll drop less voltage across the carbon pile, which means I'll have more voltage to produce an excitation field. So let's look at it in reality. So right now we have the voltage coil and the leaf spring. At my correct voltage, okay, 28 volts. So when I've got 28 volts, the electromagnetic force is equal and opposite to the spring force. Okay, so that's the datum position, the datum force for my correct voltage, 28 volts. So when I get 28 volts, the magnetic field by the voltage coil is equal and opposite to the leaf spring, the spring force, okay, pushing it up. Oh, so how does it work? Right now, I have 28 volts. So I must have also 28 volts here. 28 volts is now going to also go down this line, 28 volts. Now look what happens. I'm actually going to have an electromagnetic field, which is going to pull down. So the 28 volts here is going to produce a magnetic field, which is going to try to pull the bottom of the carbon pile down. But at the same time, the spring force is trying to push it up. Both forces are equal but opposite. So nothing happens. The carbon pile doesn't increase or decrease. Now let's look what happens when the voltage goes down. And let's say the voltage is 26 volts. Okay, again, I have 26 volts here, and I have 26 volts there. I now have less, okay, I now have less voltage at this voltage coil, which basically means the spring force is greater. And the spring pushes the carbon pile together. Okay, so let's look at what happens. So at 26 volts or low output voltage, let's see what happens in my cross-sectional area. We'll look at resistance, we'll look at the voltage drop, and we'll look at what happens to the excitation voltage. Remember, I always want 28 volts. So look what happens. I have less voltage at the voltage coil, therefore I have less electromagnetic field, which means the least spring is going to push the carbon pile together. That means my cross-sectional area must go up. They're touching more, therefore my resistance is less. The voltage drop across the carbon pile, that also is less, which means I have more excitation voltage at my excitation coil. Okay, if I have more excitation, remember we said this magnetic field, if I have more magnetic field, my voltage will go up. So what will happen is, if I have more expectation, that will now go back up to 28 volts. Okay, and then next thing, let's have a look at if the voltage goes too high. Okay, the voltage goes high. We've now got, let's call it 30 volts. We've also got 30 volts here, and we've also got 30 volts here. Now let's look at down here. I have 30 volts. So now I have increased the voltage greater than 28. So now I have more electromagnetic force than the least spring force. So now the voltage coil, its electromagnetic pull pulls down on the disc. The discs start to open up. So now we'll look at high output voltage. And we said there 30 volts. So my area, my resistance, my voltage drop, and my excitation voltage. So I've pulled the discs apart. So my cross-sectional area has gone down. That means my resistance has gone up. That means the voltage dropped across the carbon pile has gone up. That means I've got less excitation voltage. If I have less excitation voltage, I have less magnetic field, and the output of the generator starts to go down. Okay, and that's what the system does all the time. Okay, so that's the basic operation of the carbon pile voltage regulator. Now we're going to look at some basic faults. Okay, let's look at, we break the spring. Okay, I have 28 volts and I now break the spring. I've still got 28 volts here, but now I don't have a spring force. No, pushing the carbon pile together. If I have no spring force, the only force now is produced by the voltage coil, and what that's going to do is going to pull the discs apart. So if I pull the discs apart, my cross-sectional area goes up, and I mean really up. Sorry, not cross-section, goes up. Hold on, shut up, Rayburn, you're talking rubbish. My cross-sectional area, as I pull them apart, goes really down. Okay, down. That means my resistance goes really up, very high. Okay, very high. That means my voltage drop is very high, which means my excitation is very low. So basically, it could even be as low as 0, but it goes really low. Therefore, when the mechanical spring breaks, you can see that my generator will fail to a safe condition. So it's a low volts condition. Okay, not a lot we can do about it, but at least it's not causing things to catch fire. So when the leaf spring breaks, the voltage regulator, the voltage coil takes over, pulls it apart, and my excitation voltage goes to very low and probably would be nothing. So I would get no output from my generator. Now let's look at if I break the system. Okay. Let's look at if I now break any part of the circuit for the voltage coil. The only force controlling the carbon pile regulator is the spring force, and it's basically going to push the carbon pile discs together. So now look what's happened to my cross-sectional area. It's gone really up. That means my resistance across the carbon pile has gone really down. That means the voltage drop across the carbon pile is very low, which means my excitation voltage is very high. With this fault, the output of the generator, okay, will go up very big, okay, into what we call the overvolts condition. No, 32, 33, 34, 35, 40 volts. Well, so basically, in this fault, it's failed into a very unsafe condition. So we're going to have to look at something else. We're going to have to put it into the system to protect it from that. Okay, so that's the 2 voltage. So basically, if I break the leaf spring, it'll fail to a safe condition, low volts. If I break anything that controls the current in the voltage coil line, it will fail to an unsafe or over volts condition. So that's the first 2 faults. And the third one is this here called the over volts adjustment. It's a little variable resistor. And all that happens, let's say that the pilot says throughout his flight, he had a constant 29 volts. It's just a little bit high. It didn't change. It always stayed at 29 volts. Okay. This is where this over volts adjustment resistor comes in. You can actually adjust this to actually bring the voltage, the constant voltage up or the constant voltage down. My voltage is slightly too high, so 29 volts. Oh, sorry, 29 volts. So what have I got to do? I need to increase the resistance with a carbon file to reduce the excitation voltage. So to reduce the resistance, I have to push the carbon piles together. So what I've got to do is lower the voltage at the voltage coil. So in this case, I would increase the resistance. That's all. Now you're probably not going to be asked, gentlemen, which way the resistance goes up and down. But what you could be asked is, what would you do as the aircraft engineer if a pilot with an aircraft with a carbon pile regulator said his output of his generator was a constant 29 or 28 volts? You would adjust the output voltage resistor, okay? And what it allows you to, now we're going to look at this a bit more in depth later on, but what happens is this Zener diode conducts. For goodness sake. This Zener diode, so it allows when it goes below 28 volts, okay, this Zener diode stops conducting. This turns off. This turns on. I now get current going through to the excitation field. We are going to look at this a bit more in depth later on, gentlemen. So what actually happens is I pulse the field. So if I have 28 volts, so I've got my right voltage, what I'm going to have is the time that the pulse is on is equal to the time the pulse is on. So the average, okay, the average excitation voltage is correct. And we will look at this a bit more. So anyone's got any questions, I will answer them later on. We will look at this a bit more in depth later on. Okay, so don't worry about this one at the moment. We will be going through this a bit more in depth later on. So what is the advantages of solid state over this carbon pile? Well, the first thing is it doesn't have any moving parts, so it's more reliable. It doesn't break as much. It's cheaper. It's made in Hong Kong, probably Taiwan, China. So it's cheaper. It's smaller. The carbon file regulator is about that, well, quite big, and it's quite heavy. Where my voltage regulators now, they're small boxes, this size, full of electronics. They're also way less. And because we've got no chance of any sparking and arcing across these discs, we can't create any electromagnetic interference in a solid state or electronic voltage regulator. So please remember these advantages of a solid state or electronic voltage regulator over electromechanical or carbon pile. Please remember those advantages. Okay, so now we're going to look at something called generator switching. Okay, and we did have a little talk about it yesterday. Current, okay, current goes from a higher potential to a lower potential. We all agree on that, don't we? Yeah, current always goes from a high voltage to a lower voltage. Agree? Yeah. So this can cause us problems, okay? So we've actually got a rule, and we'll look at this rule in a minute. So here is my basic generator, yep. So here's my generator. Here's my buzz bar. But what else could I have on that DC buzz bar? I could have I could have a battery. And we already know that the battery is 24 volts. So now, if I close the generator switch, okay, the generator contact, but the generator is not running, so it's got 0 RPM, which basically means 0 volts. I close this. Which way is the current going to flow? I've got 24 volts and 0 volts, and the current is going to flow from the bus bar to the generator. Yep. Now, it's not going to turn it into a motor, but what it can do is it can cause some damage. It can cause some serious damage. Okay, can cause some serious damage. So, one of the rules is, oops. Again, now let's say I start my engine, okay, and my generator starts to turn, okay, and I've now got 10 volts. Now, again, I switch the generator on. I've got 24 volts. Which way is the current going to flow? It's going to flow from there to there. And this is when we remember I taught one of the faults with generator. We can't get enough voltage because the generator is switched on as we try to run it up. I will never get, the generator will never be allowed to produce enough voltage to go to the bus bar. So we call insufficient voltage. So what we need to do, gentlemen, is ensure that the generator is only online, okay, again connected to the bus bar, okay, when the voltage is high enough to be connected. What do we mean by that? What we mean, again, if I have 24 volts on my bus bar, to allow my generator to be switched or connected on what we call online, the output of the generator must be greater than the bus bar it's connecting to. So it has to be greater than 24 volts, okay? And most systems, okay, in turboprops is at least 26, but we're going to say until it gets 28 volts, we can't switch that on, okay? So what is the rule, okay, of connecting a generator to a bus bar? There it is. The generator voltage should always be higher than the battery is supplying the bus bar. The generator should always be greater than the voltage on that bus bar, okay? Voltage on that bus bar. Now, we can rely on the pilots doing that, okay? But what we can do is we can put in some devices that's going to help us ensure that the pilot can't do this, cannot connect the generator to the bus bar unless the output of the generator is greater than the voltage on the bus bar. And the device we use is called a differential cutout switch. A differential cutout switch. A differential cutout switch does two things. It helps us connect the generator to the bus bar, but is also a safety device. Okay, it's also a safety device. So we're all happy. There's my generator. There's my excitation coil. Let's look at the makeup of the differential cutout switch. There is three parts to it. There's the contact. Yep, so there's the contact. we have a series coil, and a series coil is a few turns of thick wire. Yeah. And we're talking really quite thick. No, probably 2.5, 3 centimeters in diameter. A shunt coil is many turns of thin wire. Okay, so you now know the construction of the differential cutout. The two coils, the series coil and the shunt coil. So let's look how it works. So there's the output of my generator. Okay, it comes to this point here. It's a low voltage. Okay, it's less than 24 volts. It can't flow through the series coil because this cutout contact is open, but it can go through the shunt coil, and it will start to produce a small magnetic field, but it's not strong enough to pull this contact down. When the voltage gets above 24 volts, there is now enough magnetic field in the shunt coil. So let's say 28 volts, 28 volts. There's now enough magnetic field to pull the contact down. Now, current can flow through the series coil through the cutout to the buzz bar. And as it flows through the series coil, it also produces a magnetic field. Because the current's flowing from the generator to the buzz bar, it also pulls the contact down. So basically, I've now got two magnetic fields pulling this contact down. So the series coil is really holding the contact in place. So that's how it connects. So the series coil is a few turns of thick wire, and the shunt coil is many, many, many turns of thin wire. So that's how it connects. So it doesn't allow the pilot to connect the generator until it has enough voltage from the generator to allow it to connect. So that's connection. Now let's look at the protection side. Okay. Let's say I produce a heavy, heavy load on the generator. Okay, I'm drawing lots and lots of current. And we now know if I draw lots and lots of current, the output of the generator is going to go down. Okay, and it starts to go down, and once it gets below or less than 24 volts, so it goes below 24 volts. Okay, so let's say we'll call it 23 volts out of my generator. My buzz bar, got the battery on it, that is 24 volts. Which way is the current going to flow, gentlemen? It's going to flow from the buzz bar to the generator. Okay, now it's not going to turn into a motor, but it's now going, that can cause damage to my generator. And I'm going to tell you, gentlemen, that 1 volts difference will cause an ampage of approximately 20 to 30 amps. Okay, 20 to 30 amps. Remember I said 5 amps can vaporize a lift frame in a helicopter. So what we need to do is protect the generator from that current flow going from the buzz bar to the generator. So now the current initially goes through the differential cutout switch, because that's closed. It now goes through the series coil, but it's going through the series coil in the opposite direction. And we know now about magnetic fields. The direction of the magnetic field can depend on the direction of the current flowing through the coil. So when I had higher voltage, the current flowed from the generator to the bus bar. The series coil pulled it down. Now I've got current flowing from the bus bar to the generator, therefore the current is flowing in the opposite direction. The series coil, the magnetic field by the series coil, pushes that differential cutout contact open, therefore protecting my generator. Okay, so a differential cutout switch connects my generator when the voltage is greater than the bus bar it's connecting, but will disconnect the generator from the distribution system, the bus bar, when the current flows from the bus bar to the generator at about 20 to 30 amps. Okay, remember that value. Okay, so a differential cutout will open when the current flows from the bus bar to the generator when the current is greater than 20 to 30 amps. Okay. So we're going to look at some more protection circuits. Okay. Remember, one of the protection circuits, I said, if we have an overvolts condition, we'll need a separate protection device. And we're going to look at that now.
Hello, Jan.
Yes.
I could not understand. I completely understand this function of series coil, but couldn't understand why this shunt coil is there.
Okay. The shunt coil has lots and lots of thin coils. Yep.
Okay.
And if a current goes through it, it will also produce a magnetic field. Agree with that?
Yes. Yes.
Okay. When the voltage is below 23, well, let's say when the voltage is below, let's call it 23 volts, the magnetic field, so the voltage going through here, the magnetic field is not strong enough to pull the differential cutout contact down.
Okay.
Yep. When it gets to 28 volts, the magnetic field is now greater, and therefore is enough to close that contact, allowing the generator to connect to the bus bar.
Okay.
Okay?
Okay.
Okay. So we're now going to have a quick look at some other protection devices. Okay, other protection devices. And here's the first one. Get my pen working again. Here's the first one. It's called an overvolts latch relay. Okay. When the voltage gets too high, let's call it 32 volts. And you can see here, this is connected to the carbon pile. So the current coming down from here, we'll go through the carbon pile to the excitation. That's my excitation. That's my excitation. Now, if I have 32 volts here, that will produce enough current to energize that relay. That relay opens, removing the supply to the carbon pile regulator. So if there's nothing going through the carbon pile regulator, nothing can be going through my excitation coil. Therefore, the output of my generator will go down to 0. Okay, it will fail to the safe condition. So what protects a generator from an overvolts condition, it's the overvolts latch relay. Okay, overvolts latch relay. Just look for something that says overvolts when you look at any of the answers. So that's how we protect it from overvolts, an overvolts condition. Okay. So now we've looked at that voltage trimmer that adjusts the output of the generator. We've talked about the differential cutout switch. The next thing is what we call a line contactor, and some of you will probably know this as the GCB, the generator contact breaker, the main breaker. Okay, the main breaker, and that's isolating that separates the generating side from the bus bar, which is the distribution. So basically that will connect. So it's a massive big contactor which will connect the supply from the generator to the bus bar. Okay, that's what a mainline contactor does. The next thing we're going to look at is this thing called an RCCB, reverse current cutout breaker. Some of you might have heard it's called the reverse current cutout relay. A relay and breaker, it's the same things, okay? We're calling it a breaker. Some of you might have heard it as a relay. It's the same thing. So let's look how that works, okay? So the output of the generator, let me click rid of the ink. Okay, so the output of my generator, we'll just follow it all the way up through the through the contact breaker, comes through the RCCB, through the big coil of the RCCB. And again, that is few thick turns, okay? And these are even thicker than the coils, the series coil in a differential cutout. But they're going to do the exact same job. Right now, it's just keeping that contact down. So the current flowing now keeps the contact closed. Okay, and my generator is supplying my 28 volts to my bus bar. Let's go back to a failure. Imagine now that the quill drive snaps. Okay, what's going to happen to the output of my generator? Anyone? The quill drive snaps. My generator is going to instantly stop turning. What's going to happen to the output of the generator? It's going to go immediately to zero. Yeah. Yep. I now have my battery. You can see here, there's my battery on there. So now it's gone from 28 to 24 to 0. Like that, instantly. Have I got a big potential difference, gentlemen? Yes. Okay. If I have a big potential difference, am I going to have a big current flow? I am. Okay. So if the generator output went to 0 instantly, I'm going to tell you probably 500 amps is now going to flow from the bus bar to the generator. That's going to cause a lot of smoke and fire and damage. So we need something that's going to react instantly to this condition. And this is where your reverse current cutout breaker comes in. The current is now flowing from the bus bar to the generator very fast at a high ampage. And what happens is the current goes through the coil of the reverse current cutout breaker. It pulls this contact open. And if it pulls this contact open, nothing, if I can find it, that contact opens, nothing can get to the generator. So what is the purpose of the RCCB? It's to stop current flowing from the bus bar to the generator when there's a current of 500 amps or greater flowing from the bus bar to the generator, okay? And it opens very, very fast, because if we don't do it, there'll be damage to the system, okay? So you're happy on the purpose of the RCCB? It's stopping current flowing from the bus bar to the generator, okay? The bus bar to the generator when current flows greater than 500 amps, okay? And it opens very fast, okay? So the three protection conditions we have talked about. The first one is the overvolts latch relay. It will remove the excitation voltage when the output of the generator goes too high. Okay, my differential cutout protects the generator when current flows from the bus bar to the generator when it's approximately 20 to 30 amps. And the reverse current cutout breaker operates when there is 500 amps flowing from the bus bar to the generator, and it opens very fast. Okay, so as it says here, differential cutout 20 to 30 amps. RCCB, large current 100 of amps. I said 500. It's quite easy. And the first thing I want you to now to remember, gentlemen, every time we remove the excitation field, the generator field, okay, we always take the generator offline. So remember this condition. Every time I remove the excitation field, I will take the generator offline. What we mean by that is, if I remove the excitation field, this differential contact will always open. Sorry, this mainline contactor will always open, removing the generator from the bus bar. Okay, so remember that statement. Every time I remove the excitation field, so the generator excitation field, I will always take the generator offline. Okay, I'll always take the generator offline. Remember that fact. Remove the excitation field, I will take the generator offline, remove it from the bus bar. Now, the next thing we're going to look at is something called a hold-off system. A hold-off system comes in when I put external power onto the aircraft. Okay, when I put external power onto the aircraft. It's very, very similar. The DC system is similar to the AC system, except the AC system's got a 6-pin plug. Okay, so what we're trying to do is making sure that the aircraft power supplies, whether that's the generator, the battery, is never connected to the bus bar when the external power is connected, okay? And we call that paralleling, more than two power supplies on the same bus bar. The system is called a hold-off relay, okay? A hold-off relay. It's also sometimes known as a flashback relay. A flashback relay is more an American term. So those who might go and work on things like Boeing, they might term it a flashback relay, okay? But it's what we call a hold-off relay. I'm going to be calling it a hold-off relay anyway. Okay, and this relay will make sure that the aircraft power is isolated from the bus bar when I put external power on. How does it work? Well, here's my basic system. Okay, here you can see here's my generator and here's my battery. Okay, if I've only got the battery on, I've got battery power producing 24 volts on the bus bar. If I put the generator on, I will end up with 28 volts on the bus bar. Now, my ground power supply, one of the things about ground power supplies is how accurate is the output. My output might be 27.8. My output might be 28.2 volts. Okay, this is one of the reasons why we have this hold-off relay. So let's look at how it works, okay? Let's look at how it works. So you can see here, there's my DC power supply. So those who are working on DC aircraft, you'll know this. There's three pins. There's two big ones and a small one. One of the big pins is the main 28 volts going to the bus bar. The smaller pin is a little 28 volts. Okay, we'll talk about that smaller one in a minute. And the other big one is the earth or the neutral for the power supply. So we look here, this is where my voltage is going to come in from my ground power. I have two 28 volt supply, one to the main, that's going to be carrying most of the current, and we have 28 volts to the smaller pin. The smaller pin you can see is shorter, okay? And the main reason for that is again, it's a safety device. You'll only get the system to work or connect to the aircraft when the plug is fully pushed in, okay? So we have to push the plug fully in. The next thing this little pin does, let's follow it down, okay? Let's follow it down. So I put the ground power on, it comes down to here. It comes to this hold off relay, yep. But also it's going to send voltage to the ground power relay. At the moment, the ground power relay is open, so nothing's getting to the bus bar. Even if I had my battery connected, so I've got 24 volts, okay, at the bus bar, look what happens when I switch on the external 28 volts, okay. I connect my ground power to the bus bar, but at the same time, I energize this hold off relay. Okay, I'll go back. I energize the hold off relay, and look what happens here. I open the contacts, and look, it removes the earth for the relay connecting the generator to the bus bar, and it removes the earth for the battery relay connecting the battery to the bus bar. So now you can see I have my external power (28 volts) on the bus bar. Yep. And what I can do now, I can start my engine using ground power, not having to use the batteries. And the only time, so I can run my engine up, it can start to, and my generator's attached to the engine, it can start to produce 28 volts. But I can't connect the generator to the bus bar until I switch off the external power. And as soon as I switch off the external power, the earth for my hold off relay, the earth for my generator relay is complete. My generator can now supply the 28 volts to my generator. So what's the purpose of a hold off relay? It's to make sure that we do not connect the aircraft power supplies to the bus bar when the external power is connected to my aircraft. You all happy with that? So the purpose of the hold off relay is to stop external power and aircraft power being on the same bus bar at the same time. Are we all happy with that? Good. Okay, gentlemen, I think we'll go for a quick 10-minute break. Okay, go for a quick 10-minute break and we'll come back and we're going to look at, oh, the wrong way. The wrong way, here we go. Multi-generator systems, okay? So we'll go for a 10-minute break and I'll see you in 10 minutes. Hello, gentlemen. Can you hear me? Hello, anyone hear me?
Yes.
Okay, good. Nice. Now, okay, just wait, give them a minute for people to come in. Okay, gents, we're going to look at multi, so basically two a DC generator, two engines. Okay. I'm going to call this a parallel generating system, okay? And the one advantage, big advantage of paralleling is there's no breaks in supply if a generator fails. Okay. The system can handle the switching of high transient loads. So basically, if a component, let's say, switch on a heavy motor, electrical motor, the current draw, we can actually hold the voltage up quite well. It can handle those high demands on the system. Okay. Okay, so that's the advantages of paralleling, putting more than one generator onto busbar. No breaks in supply. Okay. Next thing, it can handle heavy draws. The disadvantage is okay, that it requires extra circuitry and therefore it can make it a bit more complex. Okay. We're going to look at a multi-generation system. Okay, put two generators onto the same busbar. Oh, what's happening there? Hello, can you still hear me? Hello?
Yes, we are getting.
Yes,
Oh,
we can hear you.
okay, oh, my screen went all funny. That's good, right? As long as you can still hear me, I don't mind. Right, so we're going to look at a multi or two generator system. Okay, don't panic. Right, that's a lot of circuitry there, gentlemen. But we're going to take it down. Let's have a look what we've done. We've looked at excitation. Yeah, so we've done that. We've done that. We've looked at the differential coil. We've done that. We've talked about the mainline contactor. We've done that. We've looked at the RCCB. We've done that. We've looked at the hold off, really, or the flashback, really. We've done that. And it's exactly the same here. RCCB, mainline contactor, differential cutout, okay, and excitation and regulation. Okay, excitation and regulation. So all we've got to look at is the extra circuitry. And if you look here, we have a little coil here, okay, and a little coil there, okay. And these are called interpole windings, okay. They're called interpole. And then we've got this thing here called an equalizing circuit. Okay, there's a couple of contacts. We'll talk about them in a minute. So if you think about it, gentlemen, we're only talking about a couple of new things on this diagram. So let's talk about, I've got two generators, okay? I have two generators, and ideally, I want each of them to provide 50% of the load going to that buzz bar, okay? So, sorry, wrong way, there's arrows. So 50%, each generator provide 50%, ideally. We are allowed a difference of 60-40. So the maximum difference between loads, what we call load sharing, one generator is allowed to take a maximum of 60 and one generator is allowed to have a minimum of 40% of the load. But ideally I want it 50%. So if one generator is taking more load, the other generator is doing less. So what we need to do is get the generators to communicate with each other, allegedly. But we're going to do it through electricity. And this is where these interpole windings come in, okay? They are in series with the generator, okay? They are in series with the generator. And what we need to do, if one generator takes too much load, so let's say this one here takes 60% of the load, this one must take 40. Yep. So what I actually want to do is get this load to go down and this generator's load to go up. And this is what these interpole windings do. They can either aid or oppose the voltage coil. These, there's my voltage coil. It's just trying to keep 28 volts at my generator. That's all it's trying to do. But load, if I talk about load as in is current, okay, I need to make sure that each generator is supplying the correct amount of current. So all you need to understand, gentlemen, is what is the purpose of the interpole windings? The first thing is they have to try and get the load to be 50-50. How do they do that? They basically oppose or add to the voltage coil. So what's the purpose of the interpole windings? They are to oppose or add to the voltage coil. That's the purpose. Okay, so basically they will adjust the output of the generator to make sure my loads are balanced, and they'll be doing this all the time. Okay, so you happy what the purpose of the interpole windings are, gentlemen? is to equalize the load in a 2-generator DC system. How does it do it? Well, if one load is taking too much, it will either aid or oppose the voltage coil to get the voltage and the current correct. So that's all you really need to know. So it's not complex. You just need to understand what the purpose of the interpole windings is. And then the second part of the extra circuitry is this something called the equalizing circuit. And if you look here, the output of the generator will go through the interpole windings of each generator. So the interpole windings are in series with each other. So what we can say with the equalizing, this is where the generators can see what each other generator is producing on a load. Okay. If one load is too high, one load is too low, we'll have a potential difference. And that will cause a current to flow through these interpole windings, which causes them to aid or oppose the voltage coil. So that's the equalizing circuit. It connects the interpole windings together to allow them basically to either increase or decrease the load of the generator. And then we've got these two little contacts, okay? Two little contacts. We usually call these auxiliary contacts. We'll talk about this a little bit more later. And they're usually part of the generator contact breaker. In the normal condition, when the generators are working correctly, those contacts are closed, allowing the interpole windings to see what each generator is taking for the load. Let's look at a scenario, gentlemen. Let's look at a little another scenario. Let's say the number one generator fails. Okay, the number one generator fails. How much load is it now taking? It's a big fat zero. Okay, this generator is taking 100% of the load. And what would happen is the interpole winding on generator on the right hand side would be trying to reduce the load, and the interpole winding on the left hand side would be trying to increase its load. But if the generator has failed, it will never ever increase its load. So what will happen is more and more of the current will go through these interpole windings, and what you would end up with actually, this would, all its current, okay, all the current produced by this generator would be trying to get the interpole winding to get its output up, but it'll never do it. So what it ended up was, this would also produce zero load. So we'd actually lose everything. But this is where these equalizing circuits come in. Remember I said these are part of the generator contact breaker. And remember we said if we remove the field, the excitation field, the generator contact breaker will remove the generator from the bus bar. See, they got the line contact will open, removing. Well, these contacts are other little contacts that are actually in this line contact or generator contact breaker. They also, so when the generator fails, these open. Okay, the failed generators open. And what it does when the contact opens, it makes that generator invisible. It makes it look like it's never existed. there's no longer a series connection between the generator interpole winding on the right-hand side and the left-hand side. So now this interpole winding does nothing. And all that happens is it takes on 50% of the load. That's it, maximum 50%. So what happens when a generator fails? The contacts in the equalizing circuit open, remove the failed generator from the circuit. So we're not trying to get its load up, okay? So as you can see here, if one generator takes more load, okay? Here it says the equalizing current. We're not going to go into too much of which way it flows, okay? But you can see here it says it aids the coil in the heavy loaded, fights against the coil in the lightly, and it equalizes the outputs. So what do we take out about parallel generating systems? We have extra circuitry, and that extra circuitry is interpole windings and an equalizing circuit. Ideally, I want 50-50 load sharing on each generator, but I'm allowed a maximum of 60-40. What is the purpose of the interpole windings? They will control the load sharing. And as it says there, it will either aid or oppose its own voltage coil to equalize that load. That's all we need to think about in that. What happens if one generator fails? Then the auxiliary contacts or the contacts in the equalizing circuit open, making the failed generator invisible. And the other interpole winding is not going to try and get the failed generator's load up. Okay, so that's that. But there's one other thing, okay? And it is about, I need to draw it in. You have also here something called a boost resistor. Okay. It's called a boost resistor. So what's the purpose of a boost resistor? Well, let me tell you. When we start an engine up, okay, do we start one engine, switch on its generator, and then we start the second one? That's how we normally do it. Is that correct, gentlemen? Yeah?
Yes.
Yes. So let's say I start up generator 1, okay? Get it to my 28 volts, and I switch it on. I now have 28 volts on the buzz bar. I now I've started number 2 engine, but what was the rule about connecting a generator to a buzz bar? We had to have a higher voltage from the generator than the buzz bar it's connecting to. Remember that? So normally the generator voltage is 28 volts. But 28 volts and 28 volts are equal. The rule says the output of the generator has to be greater than the buzz bar it connects. So this is where this boost resistor comes in. It reduces, okay, it reduces the resistance, allows more current to flow through the excitation field, and artificially boosts the output of the generator to approximately 29 volts. Can I now connect number 2 to the bus bar? Yes, I can, because we've now got the rule that the generator output is greater than the bus bar it's connecting to. But we don't want 29 volts. But as soon as both generators are connected, this boost resistor shorts out, allowing my excitation field to work normally, and I produce 28 volts. So what is the purpose of the boost resistor in a DC parallel system? It artificially boosts the output of the generator to allow it to connect to a bus bar that has already been supplied by the other generator. Okay, so you're all happy on the purpose of the boost resistor? Good. Been through that. Don't worry. Yes.
The back circuit, can you please go to the back slide?
Yes.
You described the one generator fail condition, and what about this uneven load, like one is 40% and 60%? Can you explain this with the circuit diagram?
Oh no, all it is basically the regulations state that one generator, the maximum load it's allowed to take is 60%, and the minimum the other generator can take is 40%. And that's where these interpole windings would come in to share that load. Okay? So the maximum we're allowed is 60-40 load sharing. But my interpole windings would aid and oppose to get the load shared to approximately 50-50. It's going to go like this all the time. It's going to constantly move. It'll never be 50%, 50% all the time. One will go up, one will go down. So it's doing that all the time. Okay? So that's the max. That's this basic maximum minimum load sharing. And how do we do the load sharing? It is the interpole windings that are going to aid or oppose that voltage coil.
Yes, in the book there is 3 bullet points that mention in the uneven load condition, where in the lightly loaded or heavily loaded generator, how the current flows through the equalizing coil.
Yeah.
So it's better to explain in the, because I cannot getting through this bullet point. How does it function through the circuit?
Okay. Right. If I take too much load, okay, I'm drawing lots of current. What's going to happen to the voltage in my generator if I'm drawing lots and lots of current? Can you answer that question?
Yes,
Yeah.
sorry.
So what if I draw lots and lots of current from a generator? What's going to happen to the output voltage? It's going to go down. Agree with that? So when I have a heavy load, the output voltage is going to go down. Okay. So I'm going to have a smaller voltage coming out of the generator. Let's call it 26 volts. If I have less current, okay, coming out of the generator, my output is going to be slightly higher. Let's call it 30 volts. I have a potential difference. Agree with that? Yeah. So I've got 30 on the left-hand side, 26. So I'm going to have a current flow. I'm getting a. We have a current flow out of the generator. Oh, go on, give me a break. We have a current flow out through the interpole winding, so it's going to flow through it one direction. Through this equalizing circuit, and again through the other interpole winding. The other interpole winding is actually the current is going to flow in the because is wound opposite to the other interpole winding. So now looking at the voltage, I need to get that voltage down. I need to get that voltage up. That's what's going to share the current. So here, my voltage coil, okay, I need to help it, okay, to open up to get less voltage going through the carbon pile, which means I'm going to have less excitation and my voltage will come down, okay, but my load will start to go up. On here, it's going to oppose the voltage coil, okay, it's going to oppose the voltage coil. The carbon pile discs are going to come together. My output is going to go up, okay, but my load is going to go down. That's what that means, okay? But you cannot be asked that in a multiple choice quiz. That'll be 3 big answers. So we're actually wanting to understand what is the purpose of the voltage coil. Is to aid or oppose the voltage coil, i.e. the voltage regulator. So if we need to get the voltage up to get the current down, or I need to get the voltage down to get the current or load up. So that's what it's doing, okay? Hello?
Okay, Ian.
Yep.
But in the book, there's 3 bullet points. That's why it's quite difficult to,
Yeah.
realize in the circuit.
Yeah, that's why I'm trying to explain to you in quite simple terms, okay? So what I've been saying about the voltage coil, it aids or opposes to get the loads in balance, okay?
So in the generator having output high, it opposes the voltage across the voltage.
Not the output, the load. So it's getting more current taking out it, okay? So if the current goes up, the voltage will go down. Yeah, so the load goes up, the voltage of the generator will start to come down. So what we need to do is get the voltage up, that'll get the current down. And that'll do I'll do the opposite on the other generator.
Okay.
Okay?
Okay. Thank you.
Right, don't worry about that. It's just a little picture we show to the students. We get them to the basic students. But all I want to concentrate on here is now it's got the generator control unit. Okay, the generator control unit, part of that has the voltage regulator. Okay, the generator control unit, part of that is the voltage regulator. The other bit is the protection circuits throughout the aircraft. So my overvolts, differential protection, all these protection circuits also feed into this generator control unit. Okay, so the generator control unit is the brain for each generator. Okay, it's not just a voltage regulator now. So just remember that in there. So now we're going to look at AC power. Okay, we're going to look at some AC power. And I'll tell you what. Before we start, we'll go for lunch now. Do you want the full hour, gentlemen?
No.
What we say, 45 minutes.
Okay.
So catch up from this morning a little bit.
Yes. Good.
Okay. So I will see you in 45 minutes.
All right.
And then we'll start AC. Lovely. Okay. See you then. Hello, gentlemen.
Hello.
Hello. Oh, how are we all? How are we?
Good.
Good.
All good, sir. All good.
Good, 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 good. Right. Just give it a minute or two. I think a few people still to come in. Oh, there's one of them. So are many of you working tonight or tomorrow, Sunday?
Yes, tomorrow we have work, tonight no work.
Okay, so you're in tomorrow. Are you working Sunday as well?
Yes, it doesn't matter Sunday or Saturday. We get 1 or 2 days off, no matter which day.
Yeah. Yeah. That's the only problem with our well, the shifts we used to do was four days on, 4 days on, 3 days off, 4 nights, 3 days off. That's how we used to work it. Or it was, we used to work, one of the shifts patterns we actually did 14 days on, straight, followed by a week off. And then we do 14 nights. That killed you. Because time you done your 14 nights, it took you 3 days to get back to being up during the day. So you had about 2 days feeling normal. And then you had 1 day getting ready to start working the next 14 days. It was horrendous.
Yeah, the shift work is tedious.
Yeah, didn't like doing it. Anyway, hopefully I'll win our lottery tonight. Okay, our lottery, £143 million tonight. So, if I'm not here Monday, you know what's happened. I've won the lottery.
Okay, no problem.
So, I'll probably see you all Monday then.
We're happy to share the lottery.
Yeah.
Yeah, best wishes for the lottery.
Okay, I'll come out and see you first class.
So you are coming to visit Nepal then?
No, only if I win the lottery tonight.
After winning, you are planning to visit Mount Everest.
Well, I would like to do. I've not done it yet. Every time I've been to Nepal, the weather's been really, really bad.
Oh.
Last time I was there, I was staying in the hotel opposite. No, I've got this. The Hindu temples at the Bath. Bath put on the road to the airport. The big Hindu temple. I was staying in the hotel across the road from that.
Okay.
But the weather every day was rain, low cloud. So we didn't go. There were no flights round Everest that day, that week. So I've still yet to do it. Anyway, gentlemen, okay, let's continue. So we've looked at DC, okay. We've looked at AC, okay. AC is a little bit more tricky because we've got 3 different phases, okay. But it's not that difficult. So we're going to look at how we produce AC electricity, okay, what we do with it. And if we get a chance today, we'll look at how we do protection. It's very, very similar to DC, but DC doesn't have a frequency where AC does. So we might have to look at things that frequency can cause, the problems that frequency can cause. Okay, so we're going to look at AC. And as we've already said this morning, that every generator in the armature produces AC. Okay, produces AC. So actually, we don't have to do any conversion. We don't need a commutator. So far, that actually helps us. We haven't got the complexity of a commutator, and we don't have any of the losses that we can get with a commutator. There is two types of producing AC that we're going to cover, okay? When I did my apprenticeship in 1980, one of the things my instructor, just like you're getting now, told me, one of them you will never ever see, okay? One of the ways we produce electricity, you will never ever see because no one uses it. You'll never ever see it. Now I'm going to get this right. The 787 and the newer 777s have actually started to use, they've modified it. They've actually modified the system that I was told nearly 40 years ago, you will never see. So they've used technology to actually use a system that we didn't use up until, recently. So we're going to look at the two different ways of providing AC to our aircraft, okay? The first one is what's called frequency wild. This is the one I was told you will never see on another aircraft. And what happens is, with frequency wild, the frequency of the output isn't constant. We can keep the voltage the same, but the frequency of the AC changes. So depending on, and this type of generator, this frequency wild generator, is connected directly to the engine gearbox. So if it's connected directly to the engine gearbox, if the pilot puts the throttles forward, the engine speeds up. As the armature's directly connected to the engine gearbox, it rotates faster, and the frequency of my AC goes up. When the pilot puts the throttles back, the engine slows down, the engine gearbox slows down, the armature slows down, and the AC of my electricity also slows down. And this causes problems with some of our aircraft systems. Okay, we'll look at the problems and then we'll look at how we get around it. The next one is constant frequency. So basically my frequency is exactly 400 hertz. And that's the system you've got on most of your commercial, your A320s, your 737s. All use this, and you when I say the name of it, you will actually go, ah. So when I say constant frequency, the generator, we've got to have something between the generator and the engine gearbox. Because the engine, as soon as I change the speed of the engine gearbox is going to go faster or slower. So I need to put something in between the engine gearbox and the generator. And we're going to call that a constant speed drive unit. Most of you will have heard of that already, okay? A constant speed drive unit. So the first one we're going to look at is this frequency wild, okay? And as I said earlier, it's connected directly to the engine gearbox. It's connected directly to the engine gearbox. As I said there, as the engine speed changes, so will the frequency of the output. My voltage frequency changes. But what we've got to do is we've still got to make sure that the voltage is 115 volts per phase, 200 volts between the phases, or 200 volts line. That can't change, okay? We need to get this system to work later on. We need to produce this constant 115 volts. Now, when we talked about DC, if we change the speed, okay, what did we do to keep the voltage the same? We changed the magnetic field, the excitation field, and we do the exact same in AC. So if my generator speeds up, to get the output of the voltage down, my excitation voltage will come down. If my aircraft slows down, I need to get the excitation voltage up to keep that 115 volts constant. Okay, so we'll look at this frequency wild. Okay, the first thing it says, a frequency wild generator can only supply anti-icing loads on my aircraft. Why is it? Why is that? Well, let's look at the three basic electrical components I have. The first one is a capacitor. Next one is a inductor. And the third one is a resistor. What happens, okay, if we just use the word resistance, but what happens to capacity, what happens to the resistance or the reactance of a circuit if we've got a capacitor in it and we increase the frequency? The resistance goes down, so therefore I have more current. In a capacitor, if I decrease the current, the reactance, the resistance goes up. Therefore, it will decrease the current. My inductor, if I increase the frequency, I will increase the reactance, increase the resistance. If I decrease the frequency, I decrease the resistance. So the only basic electrical component that's not affected by frequency is purely resistive loads. Okay, so only loads that have a resistor, and the only things you've got looking at are pure resistive loads are the anti-icing. They're like heaters, maybe the boiler in the galley. Every other component, whether it's an LRU, a pump, will either have some sort of capacitive, an inductor. So if they will be affected by any change in frequency. So in a frequency wild generator, we could only purely directly supply resistive loads. Okay, we'd only supply purely resistive loads. The next thing is we cannot parallel them. Okay, we cannot connect two frequency wild generators to the same bus bar. Why is that? Well, I've got to have separate voltage regulators, but more importantly is the frequency. The frequency has to be correct phase rotation, so it has to go round the same way. It also has to be exactly the same frequency. any small changes in engine speed between the two engines' RPM will cause the frequency of my generator to be different from the other. So what you would actually have is constructive and destructive interference. So one would start there, one would start there. And if the frequency was different, okay, you would actually get up and down voltages. Okay, so at one point my voltage would be greater than 115, and the next minute it'll be much lower than 115. And the frequency also, the waveforms both have to start at exactly the same time. So they have to be in phase. And in this system, it's almost impossible to do. Okay, almost. So we can't, in a pure frequency while generating system, we cannot connect them in parallel. So we can't connect two generators onto the same bus bar. So how did we, when we used this system, okay, and we're talking aircraft in sort of the 1940s, how did we produce 1940s, early 1950s? How did we produce electricity for the aircraft? Well, we put everything through a TRU. Remember what I said is, we've talked about a TRU, it's just coils, primary and secondary coils. What goes in comes out. So if my voltage goes up, my output voltage goes down, up, sorry. If my input voltage goes down, my output voltage goes down. But if I can keep the voltage the same, it doesn't matter about frequency because a TRU doesn't care about frequency. So long as I can keep my 115 volts the same, it works. So the DC output from the TRU can be applied to a bus bar, and therefore we can make it like a DC powered aircraft. Okay, a DC powered aircraft. So things you've got to remember, okay? What is the disadvantages? We can only supply purely resistive loads, i.e. anti-icing, boiler, etc. We cannot put two frequency wild AC generators onto the same bus bar. And we can only supply DC to the aircraft, but it's done through TRUs. Okay, done through TRUs. If you look at any normal, if you were to look at a frequency well generator, you wouldn't see any difference, not from any normal generator. They do look the same. Okay. And it's very, very similar to the DC, apart from we don't have a commutator. So let's look at how this system works, okay? The first thing we've got to say is it is not a self-excited generator. I'm going to come back to that later. It's not a self-excited generator. So I need external power to provide the initial excitation, the initial magnetic field to excite my generator when I start. The next thing is my voltage regulator, okay? My voltage regulator here is only like a normal voltage regulator in any other generating system. It's trying to keep the voltage within its normal operating limits. Okay, when we looked at the DC generator, it was basically keeping the 28 volts. So we went up to 26, down to 26, it brought it back up. Went up to 30, it brought it back down. Excuse me a sec, I need to blow my nose. Sorry about that, gentlemen. Oh, right, thank you. Right, where was it? Yes. So my voltage regulator is looking for my normal changes in voltage due to the changes of load. Okay, bit more load, voltage goes down. I'm going to bring the excitation to get it up. If I was to say to you in a frequency well generator, I could have the throttles back at idle and my generator might only be producing 70, 75 volts. My voltage regulator can't cope with that. If I have my throttles fully forward, I could have as high as 300 volts. My voltage regulator couldn't cope with that. It's only looking for those 5 or 6 volts either side of 115 volts, maybe 10 volts either side of 115 volts. So I need something that's going to help me get the voltage of my output up no matter what the speed of my engine. It's going to get the voltage correct no matter what the speed is. And the device is going to do that is called a compounding transformer. Just think about it as a multi-tap transformer. Okay. And it can actually look at the output. This compounding transformer will look at the output of my generator. It is not interested in frequency. Okay, it's not interested in frequency at all. It's just looking at voltage. And if my voltage is low, let's call it 75 volts. So the output of the generator is 75 volts. This compounding transformer sees this and goes, right, I need to provide lots more excitation. So this 3-phase, it puts it full of a full bridge wave rectifier to convert it from AC to DC. And that will provide my excitation voltage. So it's going to I need to get the voltage up to 115 because it's very low. So I'm going to provide a very big, okay, excitation. And that will get it up. If it goes, let's say the excitation goes very high, let's call it 300 volts, again, the compounding transformer sees this and goes, right, my output's low, and basically puts a very, very low excitation field. And it brings the generator voltage down. So no matter what the speed is, the compounding transformer, okay, so we've got low RPM, we'll get a low output AC voltage. The compounding transformer will then put a large excitation current to the excitation coil to get the current, get the excitation up, get the voltage back up to 115. If the output voltage is 300 volts, again, my compounding transformer sees that. It will then put a very low excitation field to get my output of my generator back to 115. So what is the purpose of the compounding transformer? It's to compensate, okay, for changes in output voltage due to changes in engine speed. So what's the purpose of the compounding transformer in a frequency well generator? It is to provide excitation or extra excitation due to the output changing due to the engine speed. And the voltage regulator. So now if my compounding transformer, okay, manages to get my output to, let's say, 114 volts, my voltage regulator, my normal voltage regulator sees I am slightly down, and all it does is it'll put a little bit extra excitation to get my generator's output back to 115 volts. If it was 116, the voltage regulator would reduce the excitation a little bit to get it back to 115 volts. And once we have 115 volts, give or take, this GCU, my generator control unit, remember, it's a generator control unit, GCU, is voltage regulator and a lot of protection circuits. And once it's happy, it will close the line contactor, or we'll look at it later on, GCB, generator control breaker, contact breaker. And it will allow this 115 volts to go to my anti-icing systems, my purely resistive loads, and my 115 will go to my TRU to produce my DC. So how do we power systems that are not resistive in a frequency wild system? We send the voltage through a TRU to produce a DC voltage. Okay, so far, what do we know? Compounding transformer, the generator, frequency wild generator, its output changes with engine speed. The higher the engine speed, the higher the voltage it produces. The lower the engine speed, the lower the voltage it produces. My voltage regulator can only compensate for small changes due to different loads being switched on and off. My compounding transformer, it does the compensation, provides extra excitation to compensate for the voltage produced due to different engine speeds. So we're all happy on those things. What does the voltage regulator do in a frequency wild? It just provides excitation for small changes due to normal load use. Compounding transformer compensates or increases or decreases the voltage due to changes, the lab voltage changes due to changes in engine speed. Okay, so that's operation art. You're happy on the three main parts: the voltage regulator, what the voltage regulator does, what the compounding transformer does, and what type of loads we produce. or what type of loads we can supply. Are we all happy on that? Yep, good.
Yes, sir.
Hello, Ian.
Okay, thank you very much.
Hello.
Now, I said it was not what was called a self-excited. It doesn't produce its own voltage to produce its own excitation on startup. So what we have to do is basically, this generator is what's called an external excited generator. So what we have to do, we have to either use a power supply, okay? Use a power supply, and if you look at this, the switch on the generator switch, it's a 3-position switch. We would put the 3-position switch to reset. These relays would close. And if you can see here, I'd get a current all the way through to provide my excitation. Okay, so that's all we need to know. What's one of the disadvantages? We talked about that. It's not a self-excited generator. It is an externally excited generator. Once it's up and run, you put it to the normal on position and it works like any other generator. Okay. So what do we need to know? What is the purpose of a compounding transformer? Compensates for the voltage produced due to changes in engine speed. The voltage regulator just provides voltage regulation for normal changes in load. What systems can I supply? It's either purely resistive or other loads via a TRU. What's the one big disadvantage? It's not self-excited. Okay, are we all happy in that information on a frequency wild generator? All good? Good. Now, as I said earlier on, you probably won't see a pure frequency wild generator, but we're going to look at later on this afternoon. We're going to take this concept and we're going to make it modern to supply aircraft, and we'll look at why it is later on. Okay, so it's an externally excited generator, and the voltage regulator performs poorly for the large changes, and that's why we have a compounding transformer. Okay, so that's the basic frequency wild generator. Let me just follow the notes. Now, the next one you've got in your book is the constant frequency. The big advantage of a constant frequency generator is not only is the voltage constant, but so is the frequency. And if the frequency is constant, I can use it on components that have capacitors and inductors. Because the designer, if a system requires AC electricity, the designer puts all the electronic components in there and works it out that the frequency of the AC it's going to use is 400 hertz. It's never going to change, so we don't have to worry about frequency. But we need to worry about how we keep it at a constant frequency. So as we says here, frequency is determined by the rotational speed of the armature. Okay. Most generators, okay, and I just say most, that you've got on the back of your engine gearboxes go at approximately, the armature rotates at approximately 8,000 RPM. So we're going to keep that armature spinning at a constant speed. That constant speed will give me my 400 hertz. So now we can actually supply resistive and reactive, capacitive and inductive loads. And it also means if I want, I could put this into a parallel aircraft generating system. So an aircraft that has more than three or more generators. We don't cover what's called synchronizing on this course. You'll do that on a type course. But we need constant frequency generators to connect into a paralleled AC distribution system. And again, those who are working on it, your A320s, okay, as well as larger helicopters. And the 1.3 people, we'll look at how we supply this constant frequency on large helicopters, not the small ones you have, but on the large ones. And there we are, gentlemen. There's what's written on most of your aircraft that are AC. 115 phase, 200 volts line, 3 phase at 400 hertz. Okay, 400 hertz. And again, now we're going to divide this down into two ways we can create AC. The first one, this is the one you've got, those who are working on the A320, this is what you've got fitted, the constant speed drive unit. It's a hydraulic, mechanical, electrical device that will actually keep the armature speed constant no matter the speed of the engine gearbox. And this one is called a variable speed constant frequency generator. This variable speed constant frequency generator is basically a frequency wild generator. But we're going to do some electronic magic to produce an AC voltage, no matter, with a constant frequency, no matter the speed of the engine. So we're going to use some electronics. We'll look at both these systems this afternoon. So let's have a little look at the constant speed drive unit. Okay, it used to come as two parts, the generator and a constant speed drive unit. They were bolted together and they were connected, as you can see there, onto the engine gearbox. In many aircraft now, they come as one unit. Okay, they come as one unit, and that unit we call an integrated drive unit. Okay, is that what it's called on the A320s? Do you call it the constant speed drive unit or the IDG, integrated drive unit?
Yes.
IDG.
IDG, yeah.
Yeah.
But you are aware it's two components in one. Okay. So thank you very much for that information. So let's have a look at it. Okay, there's two parts. The bit at the back, that's my generator. Okay. The bit at the front, that's my constant speed drive unit. Put them together, it's an integrated drive unit. Now, I did say it's a mechanical device. It has hydraulics inside, okay? Has hydraulics inside. And just like any other hydraulic system, if the level is not correct, it won't operate correctly. It's just like if you go very low hydraulics, below minimum, your hydraulic system won't work very efficiently. And it's just like that in a constant speed drive unit. So when you go to do any inspections on it, it's important you look at the oil level, okay? The oil level must be correct. There must be no signs of oil leakage, etc. So what's the purpose of the constant speed drive unit? Okay, it's to drive the generator, and I use the word generator armature at a constant RPM for varying various engine speeds. Okay, what is it? It is a hydro-mechanical device. Okay, it's a hydro-mechanical device. Oops. We're going to have a look at we're only looking at basically how this system works. Okay, they're quite complex machines. We're just going to look at it basically. So here is our hydromechanical device. Okay, my hydromechanical device. We're just going to point out a few. There's my reservoir where the oil level is going to be. We have this thing here called a mechanical governor. Okay, and a mechanical governor, what it's going to do is actually going to put pressure or direct pressure either side of that piston to cause that piston to move to the left or to the right. And that piston is connected to a swash plate. Swash plate is going to move in or out. And as that swash plate moves in and out, it's going to increase or decrease the pump rate on this hydraulic pump. That hydraulic pump is connected to a hydraulic rotor, and that hydraulic rotor is connected to the generator. So no matter what the speed coming in from my engine gearbox, at my generator, okay, my generator, its RPM is going to be constant, and it will give me a constant 400 hertz. We want to look at that. And we're going to look at some of the safety devices that are actually incorporated or in the constant speed drive unit as well. So let's have a quick look at how the system might work, okay? So now you can see there is my input from the engine gearbox. To be honest, it's only one engine input. It's just different cogs coming off driving different things. So let's look what happens. Let's say my engine speeds up, okay? My engine speeds up. I need to make sure for a fraction of a second, okay, for a fraction of a second, the frequency starts to go up 2, 3, 4 hertz. It goes up a couple of hertz, not big amount, but a couple of hertz. Now I need to get this hydraulic pump to slow down. Okay, so what is going to happen is the pressure either side of this piston is going to cause this swash plate to tilt in. Therefore, it's not the pump is not as far. Therefore, the pressure it produces is less. If there's less pressure from the hydraulic pump, the hydraulic rotor slows down. And if the hydraulic rotor slows down, that small increase goes, and I come back to 400 hertz. Let's look at if the engine starts to slow down. So the engine gearbox, it also starts to slow down. The mechanical governor is going to put pressure either side of this piston. Now, I need this hydraulic pump to work harder. So the mechanical governor is going to move the piston to move the swash plate further out. Okay. And now the stroke rate, the length of that stroke is longer. Therefore, the hydraulic pressure in here is higher. The hydraulic rotor speeds up and gets that small drop of frequency for that fraction of a second back up to 400 hertz. In reality, gentlemen, this could be moving constantly. Now, the next thing you said here, look here, it calls magnetic trim, okay? Magnetic trim. That is an input from the voltage regulator, and we'll be looking at what that does later on. So please remember, when we talk about the magnetic trim, it's actually going to very, very gently change the pressure either side of this piston. So it's going to minutely change the distance that this swash plate is moving. Okay, so the mechanical governor is basically, okay, like the compounding transformer. It's going to compensate for the large changes in voltage or large changes due to the engine speed. The magnetic trim comes from the voltage regulator for the small changes that we need to do. Okay, so that's the basic operation of my constant speed drive unit. Let's look at some safety devices. Okay, in there, the constant speed drive units, there'll be systems that are monitoring at least two things. Okay, the two basic things are oil pressure and temperature. Okay, and of course, if the hydraulic oil starts to go down, that pressure is going to drop. At the same time, my temperature might go up. So if I've got some bearings or there's mechanical wear, this temperature can go up. Now, these will be connected to warning lights in the cockpit or to control a caption on the ECAM or ECAM or ECAS system in your aircraft. And when the pilot sees he either has a low pressure warning or a high temperature, it gives him the option to manually disconnect the drive from the engine gearbox to the constant speed drive unit. Okay, and all it does in this, it says here the constant speed drive unit, the CSDU disconnect. There's an electromechanical clutch. Boom. All you do when he pushes the disconnect, it basically separates the drive. Okay, there's a clutch. So it separates the clutch, and no longer is the engine driving the constant speed drive unit. Yes, you lose your AC, but again, it's better than the constant speed drive unit damaging your engine. So that is the manual way. So if the pilot sees that the temperature or the oil pressure are incorrect, he has the ability to manually disconnect the constant speed drive unit. But we can get to situations where either there could be a fault that can happen very, very quickly, and then we don't want the pilot to have time to make a decision. So we have two automatic safety devices. The first one is a quill drive. It basically shears. Okay, so if the bearings, any of the bearings or any of the mechanical components seized, would get that torque force, that shear force, and it would disconnect. Okay, you don't have to remember any values. That would change between different constant speed drive units. But all you have to remember is if the torque or the shear force exceeds what's required, that quill drive will shear, disconnecting the constant speed drive unit from the engine. We've also got somewhere again in this disconnect, we have something called a eutatic solder joint. Okay, again, it's another joint, but basically it's soldered together. It's a high temperature solder. It's not like the solder you get when you're soldering electronics, but it's blob. And it's quite solid until a preset temperature has reached. And when it exceeds that preset, that solder starts to become soft until it becomes so soft. Again, the eutatic solder joint melts and breaks. Okay, so we have two ways of disconnecting the constant speed drive unit from the engine. The first one is the manual, and the pilot pushes the disconnect button and the clutch opens. We have two automatic ways of disconnecting. One, when it exceeds a shear force, the drive shears. Or when it goes above a set temperature, that eutatic solder joint melts and the shaft, the two shafts just basically separate. Okay. So we're happy about the safety devices in a constant speed drive unit. Yeah? Yes? No? Good.
Yes.
Yes, thank you.
Yes, sir.
Thank you very much. Now,
This shear
those who have
disconnect means,
say that again?
this shear disconnect means it's a quill drive.
Yeah, it could be a quill drive, or it could be a weak piece somewhere in there, one of the shafts inside. Okay, it doesn't matter. Somewhere in the shaft will break when you go above a certain shear force. Okay, doesn't matter where it is, it just will shear. It could be a quill drive, it could be actually in the constant speed drive unit itself.
Okay.
Again, it'll change between aircraft. Okay, it will change between aircraft, but there will be a shear force. Now, those who work on the A320, if the pilot was to manually disconnect the constant speed drive unit, it would call you out. You would do your checks. If you found nothing wrong, you can reconnect this clutch. Okay. Now, I believe on the A320 is a little panel and you pull a chain. Is that correct?
No.
Those who work, pardon?
There is no such type of chain.
Oh, or is that a key? You got the key?
Yes.
Yes, right. I'm getting mixed up from the 737 has a little chain to read. So in the A320, you have a key you put in and you reset the clutch. Okay. just be aware. Now, gentlemen, I'm going to remember, this course is designed for people who have never worked on an aircraft, never mind working on a bicycle. Some of them haven't even worked on a bicycle before. So one of the things is, when would you reset the constant speed drive unit? It's going to be with the engine stopped and the aircraft on the ground. Okay? Remember, this is for people who have never done any aircraft. I would like to see any of you reset the constant speed drive unit at 30,000 feet with the engine still running. Okay? I will pay good money to see you do that. Okay? So when do we reset the constant speed drive unit if it has been manually separated, is on the ground with the engine shut down? Okay, so please remember that. Not that you would ever try to reconnect it with engines running or in the air. Yes.
Me, can you explain once again acoustic solder, that one once again?
Okay. So we'll just go. There's a drive. Okay, so what we're going to have is a drive shaft. So basically this engine, use static solder joint. Okay, there's one drive shaft. There's the other drive shaft. And what this connection is, got this solder joint. This joint is soldered. It's a high temperature solder. It's quite a solid solder. Yep. So the two drive shafts are soldered together. Yep. But we know when solder gets hot, it'll eventually melt. But before it melts, it becomes soft. And if the drive shaft, it'll get to the point where the solder's so soft that the drive shafts separate. Does that answer your question?
But it does automatically?
Yes, because if the temperature anywhere in the constant speed drive unit goes above a set temperature, that eutatic solder joint, and I think it's about 160 something degrees, but we don't need to know that, goes above a set temperature, that solder becomes soft and the two drive shafts will separate. Okay?
Yes, sir.
Okay, thank you. Where are we? So, what do we need to know? If the engine speeds up, the mechanical drop governor senses this, underdrives the hydraulic motor, reducing the speed of the hydraulic rotor, and the frequency goes down. And the last bit is the governor is insensitive, so fine control is done by the generator control unit. Okay, the generator control at GCU. Again, the voltage regulator. So the fine trim, any small changes in voltage due to loads, we can actually take out in this magnetic trim. But we'll look at that later on. Okay, so the constant speed drive unit will disconnect manually when the oil temperature, oil pressure of the true is detected by the pilots or the flight engineer or the crew. Okay, manually disconnected. Disengage the clutch. Automatically, okay, when the temperature, don't worry about remembering the temperature. Okay, I think I said 163 a minute ago. Basically, when the temperature goes above a set limit and the shear force exceeds a set amount, you do not need to know any figures, okay? Just know that if the shear force is too high, it will shear. If the temperature is too high, that eutatic solder joint melts. And the system can only be reset on the ground only. Can only be reset on the ground only. Okay. Any questions on the constant speed drive unit, gentlemen? No. Right, here are we? So what we'll do is we'll go for a 10-minute break. Okay, we've been sat down for well over an hour now. We'll go for a 10-minute break. Okay, and we will come back and have a quick recap of what else we need to do today. Okay, so we'll go for a 10-minute break. Hello, gentlemen. Okay, we're all ready to go again?
Yes.
Thank you. Right. So we're now going to look at something called the brushless AC generator. Okay. You'll see as a diagram on the screen. This block diagram you will see in every type course you will do when you talk about those who are working on AC aircraft. This will come up many, many times. But we'll look at it, just get a basic understanding. So this is what's called a self-excited, okay, AC. Oh. So this is what we call, okay, this is what we call a self-excited AC brushless generator. And again, this is the AC. This is the brushless. This is the generator you will find on connected to most integrated drive units. So we don't need to worry about any brushes picking up any electricity. It's all done through induction. Okay, all done through induction. So there we go. Brushes, no wear, don't need to take them. Those who work on turboprops, one of the biggest problems is constantly checking the brush wear. And it has less moving parts, therefore it's more reliable. So let's have a look how the system works. Okay. The first thing is we need, this thing is also what's called self-powered. It's self-excited, but it's also self-powered. And it's all done by this. I get it. Okay, it's all done by this. This basically says rotor. This rotor, okay, so everything inside this dotted line is basically inside the generator. This is the bit it's going to rotate, okay? It's all part of the armature, okay? But in this armature, we have 3 sections, okay? It's just like an amplifier, okay? Those who have got good stereos in your house, you know you don't go from the CD to big speakers. You have several steps in between. You're amplifying steps. This is what we're going to do with an AC brushless generator. So it starts off, if I was to put here, that is the shaft going to the engine, okay, or the engine gearbox. So this, everything inside this dotted line is rotating. Everything on the outside is on the case of the generator or inside or attached to the case. So now this here is what's called a permanent magnet generator. It's usually, it looks like it's shaped like a gear, a cog. It's a 12-pole permanent magnet. It's a permanent magnet. Let's go back to basic electricity. If a permanent magnet, the magnetic field caused by a permanent magnet cutting a conductor, you hear this bit here, this coil here, it's going to produce a, what type of voltage, AC or DC? Anyone? A rotating permanent magnet cuts a conductor, is going to produce a AC voltage. Thank you very much. Yeah, thank you. My GCU, remember, generator control unit, the voltage regulator part of that, what it does, it looks for that AC voltage. And it also knows Once it gets to a constant RPM, I will get a voltage, and it looks for the minimum voltage. Okay, we don't need to know what it is. To be honest, I can't remember off the top of my head myself. But it looks for a voltage, and once it gets that AC voltage, it goes, right, the generator is now running at the correct RPM. And once it does that, it sends now a DC to this coil, and this coil is known as the excitation field, the exciter field. The bit it's going to produce increase or decrease my voltage. So this is where the voltage regulation is done. So it's now producing a DC voltage. And now I have this three-phase coil cutting my electromagnet. So inside this, what we call the exciter generator, the second stage in the rotor, we produce an AC. Okay, and we take that AC and we put it through this full wave bridge rectifier. And if I put an AC through a full bridge wave rectifier, it creates a DC. Okay, and that's on the third stage of the rotor. That's at the back of the rotor. And so this DC creates a magnetic field, okay? But this magnetic field now rotates, and see these coils here? These are the coils that are on the case of my generator. And into there, I will induce an AC. An AC of 115 volts, yeah, for each phase, at a frequency of 400 hertz. Okay. So what can we take out of this? Remember, it's self-excited. It produces its own power to start up and provide its own excitation. And what provides its power is this thing called the permanent magnet generator. If it loses its magnetic field or breaks, it will not work. Okay, and again, I have never known one of those break ever. Okay. So what's the purpose of the PMG? It's basically supplying power. It's providing power to provide my self-excitement for my generator to produce its output. Okay, so remember that. What produces, or what's the purpose, or what produces the power for my brushless AC generator? It's this one here, the PMG. Okay. All happy on the operation of an AC brushless generator, gentlemen? Okay, good. Yes, Chris.
Yeah, in this slide, 2 GCU AC and then is DC from GCU.
Yes.
The upper one. Can you explain this once again?
Okay. Remember, the GCU is part of it is the voltage regulator. Part of it is going to be protection devices, which we'll look at this afternoon. But what I can see is, get it? This is one box. Yep. So in here, it's looking for a minimum voltage because that's rotating. So that's going to be provide a minimum. And once the GCU sees it has a minimum voltage of AC, Yep. The GCU now knows that the generator is at its normal operating speed. And it uses this, and in here again, there'll be a bridge rectifier, yep, to convert the AC into a DC. And that DC here will have a one-way, so that could be like a north, and that's an electromagnetic field. Okay, and the center part, the excitation generator, it's rotating, its coils are rotating through that magnetic field. Okay, producing the AC. Okay.
Yeah, I understand now.
Okay, no problem.
Yeah.
So everyone else happy? Good. Yes.
This to the GCU, the AC supply is from PMG. So in the case of the supply, if the generator is not running,
It's not running. There'll be nothing there.
It won't get supply from anywhere.
You're probably going to find in reality the electronics will be supplied maybe from the battery or the ground power system.
Exactly.
But in theory, this brushless generator can self-power itself, okay? In reality, you might have power from the battery or the ground power.
Yeah.
But in theory, this could self-power itself, okay? So the voltage regulator, the GCU, could be completely powered by that. So once it's got enough voltage, it's going to power the electronics in the voltage regulator, and it's also going to supply that DC current. But we're just looking at it from a basic block level, okay? We're just looking at the basic understanding of a brushless AC generator, TR. You happy on that?
Okay.
Good. Right. Now, the last generator we're going to talk about. Hurrah! Okay. It's something called a variable speed constant frequency generator. This is a basic frequency wild generator with electronics. So what can I say about a variable speed constant frequency generator? It's connected directly to the engine gearbox. Okay. So now if the engine speeds up, the armature speeds up. If the engine slows down, the armature slows down. But what we do in there will eventually, coming out the back of this variable speed constant frequency generator, give me 115 volts, 400 hertz, three-phase AC. Okay. Now remember I said it is basically a frequency wild generator, which is the bit it's directly connected to the engine. And then I said it has electronics. Okay. In this area you can see, there we go, the bite, you know, the self-test. So we've got electronics. Let's look at this system. Okay. Just like other generators, it actually has oil in it. Again, we need to make sure that that oil level is correct. Okay. We'll look at the electronics in a minute. But in here, we're going to have lots of we've got transformers, electronics, on top of the normal current produced in a generator. Now, in most basic generators, you can literally have a fan attached to the armature and it'll actually suck or blow air over the armature to cool it down. On this, we need to have cooled air because it gets really hot. Okay, so you can see here, we actually have an inlet from cool. So it's got a cooling system somewhere in the aircraft to blow cold air in over the armature and the electronics, and it will go out. Okay, and then, as I said, we've got these electronics. We'll look at that later. So let's look how it works, okay? It's a basic frequency while generator, okay? And you can see there it's connected directly to the engine gearbox. So now we know that if the engine speed changes, the frequency is going to go up and down, and so is the voltage. Okay, and in a frequency while generator before, we've got something we're going to control the voltage. So let's look how it works. So here's a basic block diagram of the stages in my simple variable speed constant frequency generator. Okay, so let's look at the first bit. There's my GCU, okay, my generator control unit. You can see the first thing is, look, there's a supply from the PMG, the permanent magnet generator. So we can actually say it's a brushless AC generator. There's no brushes. And look, from the GCU, there's my excitation field. So just like the frequency wild, what we're going to do is we're going to control the excitation depending on the speed of the engine. So if the speed of the engine goes down, I'm going to provide a, so if the speed so RPM goes down, my excitation field is going to go up. RPM, okay, goes up, my excitation field is going down. And that's no any different from we looked at the frequency while generator. So coming out of my frequency while generator, I have a voltage of 115 volts, but the frequency can be up or down. Okay, it can be literally as low as a couple of 100 hertz up to over 1,000 hertz. So now we've got an AC, we've got the correct value of AC, but the frequency is not good. So I cannot use it in all my aircraft systems. So what are we going to do? We're going to put it through a rectifier. We're going to convert it to DC. Okay, we're going to convert it to DC. And we take that DC, we take that value of DC, and we put it through, this is where the electronics come. We put it through what's called a static inverter. Using electronics, I change my DC waveform, okay, and I have three DC values, or 3 lines of DC. Each one of them I will put through the inverter. And what this inverter does, it produces an AC, an alternating current, but it produces it in the form of a square, or what it says there, a pulsed waveform. It's a square wave. My electronics, my motors, my aircraft systems don't work on square wave, they work on sine wave. And remember we talked earlier on about and we're doing avionics, so those who've done avionics, a square wave has multiple or infinite number of sine waves, but the fundamental frequency is the frequency of the square wave. So what we do is we take that square wave and we pass it through an electronic filter. And what the electronic filter does, it only allows the sine wave, the fundamental frequency of 400 Hertz through that AC filter. That square wave is 400 Hertz. The fundamental frequency is actually, okay, that sine wave in there. So we take the filter, we only allow the sine wave to pass. So coming out of here, I get 3-phase, 115 volts, 400 Hertz. So that's the basic block diagram. Generator, rectifier, inverter, filter. Remember the 4 stages of a variable speed, constant frequency. Generator, AC. Inverter, DC. So rectifier, DC. Inverter, square wave. Filter, sine wave. Okay, remember that 4 stages. But let's look at how we get that voltage. Okay, let's how we get that voltage. Let's look at the generator control unit. As you can see here, it's monitoring the output from the PMG. So it's looking at the output. It's also looking what's coming out of the rectifier. It's also looking what's coming out of the inverter, and it's also looking what's coming out of the filter. So every stage of the variable speed constant frequency, the generator control unit is monitoring. But the generator control unit only actively controls 2 parts. The excitation field and the frequency control of the electronics. Okay? Because it's looking here at that frequency coming from the AC filter. If it's not quite 400 Hertz, it will cause this inverter to either flip the AC a bit faster or flip the DC a bit slower. So, what 2 stages does the generator control unit actively modify? It is the excitation field to the generator and the frequency control of the inverter. So that's the basic part of that diagram. So what do we need to remember? Okay, what do we need to remember? Well, the first thing is the basic block diagram for a variable speed constant frequency. The 4 stages: generator, AC, variable frequency. Rectifier produces DC. Inverter produces a square wave, and the filter produces the sine wave, 115 volts, 3-phase, 400 Hertz. The GCU monitors every stage of the variable speed constant frequency generator, but only modifies 2 stages. That is the excitation for the basic generator, the frequency well generated part, and the frequency coming out of the square wave coming out of the inverter. So remember the block diagram, the 4 stages: generator, rectifier, inverter, filter. And what 2 stages does the GCU, the generator control unit, actively modify? Oh, sorry, missed this. Hold on. So, are we all happy about the operation of a variable speed, constant frequency generator, the 4 stages, and what the GCU actively controls? Are we all happy with that?
Yes, sir.
Good,
Yeah.
thank you.
And
Right.
do you have to remember this 270 volt DC, this value as well?
No, don't worry about the voltages. Just remember the actual stages, okay? Just remember the stages, okay?
Oh,
Just remember the stages.
thank you.
So now we're looking at what if you're going to check maintenance for. The first thing, the big thing, oil leaks. Okay? Oil leaks. That's part of the cooling system. Any damage, security, it's not loose. Signs of overheating, like the casing, or gets that bluing when you get signs of overheating. Cleanliness and security of the cables, yeah. And I emphasize it again, oil level, okay? So, of all the generators, the frequency wild, the constant speed drive unit, the variable speed constant frequency, because they all require oil for cooling or for operation, oil level is one of the things you have to check, okay? You have to check. As I said, because it's got electronics, we're going to have some sort of self-test facility, okay? So we've got my built-in test, my bite test, okay? And there's 3 reasons to carry this out. Gentlemen, I bet you could actually remember every single one of these 3 reasons if they give you a sheet now. If the system was unserviceable, it was malfunction. You all there? All right, the first thing I'm going to do, most of the aircraft now, I'm going to do the self-test. See what's wrong. The next thing, it says low residual voltage. You wouldn't know about that because it's a malfunction, but just remember low residual voltage. And the third one, if it's part of scheduled maintenance, okay? Scheduled maintenance, as it says there, the bite check comes from the bite check supply comes from the low oil pressure light. Why the low oil pressure? Okay. Am I going to do the bite check with the engines running? No. So basically, when the low oil pressure light comes on, because it's not running, that's where we get the power. Okay, so it's an interlock, it's a safety device to stop you playing about with it when it's running. Okay, so that's that. So are we all happy on the variable speed, constant frequency generator?
Yeah.
Okay, good, thank you. Yes, Chris.
How these generators are installed? It's not you covered, though I'm asking simply. With some V clamps or gaskets are used.
That would be in accordance with your maintenance manual. It could be V clamps. It could be bolted on. Okay, that would be type. Okay, type course, how it's connected. That'd be done in accordance with your maintenance manual. Okay.
The gaskets are used or not?
I would expect so. Yes, I would expect there'd be gaskets of some sort. Okay. Okay, but that would be in your maintenance manual. How you physically would connect your generator to your aircraft, the correct procedure would be in the aircraft maintenance manual. Okay, Chris?
Okay.
Right, lovely. So next thing we're going to look at, okay, is it just check on your notes, gentlemen? Is it protection devices next, or is it the bus power control unit?
It's simple fault conditions.
Right. Okay. Yeah. So I'll just go back. Right. So what we're going to look at is some basic faults. Okay, some basic faults in our aircraft and how. Okay, and how we protect the aircraft and the generating system itself. Okay, we're going to look at this. So the first thing is certain loads, okay, they might not have a temperature control, okay? They might not have a temperature control. And therefore, when it's on the ground, when you think about it, I'm flying, let's give an example. My windshield anti-ice, okay? My windshield anti-ice. My windshield anti-ice is designed to keep the frost and the snow off my windshield when I'm flying through cloud and snow at 300, 400, 500 knots. Okay, or if I've got lots of snow on the ground where it's nice and cold, like Scotland right now. So when it's flying and it's cold at 36,000 feet, it's minus 56 degrees, approximately. So what are the chances of my windshield anti-icing overheating at 36,000 feet? It's not going to happen. On the ground, okay, if I was to put my windshield anti-icing on, it might cause damage, okay? So what we're actually going to do in quite a lot of aircraft, the voltage might differ between aircraft, but we're just going to say 75. The weight on wheel switch will connect to these heated systems and will drop the voltage from light. Because some of the windshield anti-icing systems now can be 115 volts, and there's some of them now in the modern aircraft, it's 415 volts. Going to tell you something happened. Now, I was working out in Oman in summer. Okay, so has any of you been to the Middle East? Okay, Dubai, UAE, Saudi Arabia. Anyone? No. Well, I can tell you, gentlemen. Yeah, what's that?
No.
No. Okay. I can tell you, gentlemen, in summer, the temperature can get to 55 degrees centigrade. When I was out there, one of the young mechanics went out to do a quick functional. But when he put the external power, when he put the AC on the helicopter, he didn't check his cockpit switches correctly. And he was sitting there doing a quick functional, and then there was this almighty crack as the windshield cracked from the top left all the way down to the bottom right. We all heard it. We all looked around and went, oh. And what had happened is he forgot, because the aircraft had gone up several thousand feet onto the mountains, it was a bit misty, it was a bit cold, so the pilot put on his windshield anti-icing. He landed on, forgot to switch it off. The young mechanic went out and put the power on, didn't fully check his cockpit switches, and the windshield anti-icing came on at full power. 55 degrees centigrade, plus the sun, plus the windshield. We had 115 volts going through the windshield anti-icing. It overheated very quickly and cracked. And as you all know, the windshield is part of the primary structure, so we had to fix it. If we'd had this system where the heater dropped to a lower voltage, there was probably a chance we would not have cracked the windshield. But my aircraft didn't have this system to drop the voltage to 75 volts. So how can we protect your heated systems? We have a weight on wheel switch, which drops the voltage to my heating systems to a low level, and we are saying 75 volts. Okay, so that's how we protect it from overheating. So things like windshield anti-icing, we stop it from overheating. The next thing we're going to look at is all these different faults. Overheat, earth leakage, we'll look at what an earth leakage is. Undervolts, over voltage, overload protection, and something called differential protection. Okay, differential protection. So let's have a quick look at the first one. Okay, the first one is overheating. My generator is overheating. What could cause that? Well, there's the first one, normally due to poor cooling. Now we saw in the variable speed constant frequency, it actually had an external cooling system coming in to cool the generator down. Most generators have got some sort of fan attached to the armature shaft, and it rotates, either sucks cold air across the generator armature or blows cold air over the generator armature. But you might get to the point where the generator is going to overheat. Okay, the generator is going to overheat. So what we're going to have is basically called a temperature sensitive switch. Now, it could be as complicated as some high-tech electronics, or it could be as simple as, it says there, a temperature switch will provide a logic 1 or a logic 0. Here's my generator overheat light or caption. And on here, okay, if I put a bimetallic switch, yep, bimetallic switch. You're not happy what a bimetallic switch is. It's two metals bonded together. And as they both expand at different rates with heat. So basically the metal will curve. So now if I have this temperature switch or my bimetallic switch on the, let's say as the temperature goes up, it will get to the point where that switch will bend over, completing the circuit, and I'll get my light or my caption in the cockpit, or on my, or puts a warning up in the ECAM or ECAS system. It's as simple as that. It could be as simple as that. But where do we place this temperature sensor? We're saying we put it in the exhaust. Okay, so where the hold on, going too far. So where the air comes out of the generator is where we're going to put it. Why do I put it in the exhaust? Why don't I put it on the case? Okay. If I look at my generator, there's my case, okay, and there's my armature, and there's the exhaust, okay. So there's the exhaust going out to the atmosphere. So I'm pulling air in across the armature. If I put it on the case, okay, by the time the case gets too hot, because you've got that gap and you've also got cooling air, the temperature before, as the temperature here gets above on the case becomes too hot, on the armature, it's really hot. It's way over. But if I put the sensor in the exhaust, as the air heats up, it instantly is affecting this temperature sensor. So we actually put the temperature sensor in the exhaust of the generator, okay? Or wherever the air leaves the generator. We don't put it on the case. And if we did have an overheat and we still left it on the case, if the overheat went, the heat is contained in the case. So this overheat condition, even though it had cleared, would still be indicating an overheat condition. So the temperature sensor for generator overheat is always put in the generator exhaust. Always put in the generator exhaust. Next thing we're going to look about is something called earth leakage. Okay, you might not have heard that phrase. Another phrase you might have heard is something called a feeder fault. If you haven't heard of that, you've definitely heard of this. Okay, an earth leakage, okay, is the technical term for a short circuit. Okay, is the technical term for a short circuit. So that's what an earth leakage is. Okay, so it says there, if there's a problem with the insulation, okay, the current would be in the neutral line. We'll look at this. I'm going to explain this in a minute. It's going to be sensed and it's going to inform the crew. Okay, it's going to put a warning light in the cabin, or it's going to put a caption up on your ECAM or ECAS system. It can cause wear on the generator bearings, which could transfer onto through to the engine. Okay, and it's just like when you get a car, you get to get a new tire on. The last thing you do is get the wheels balanced so you don't get that wobble. That is what you can get in a generator. gentlemen, I'm speaking to, well, everyone, but specifically the helicopter people. Now, in an A320, if the generator, what we call, is out of balance, the rotor is either electrically or mechanically out of balance. It will provide a vibration. Okay? It will provide a vibration. Hello? Hello? Oh. It will provide a vibration. On an A320, like some of you are working on, you wouldn't feel the vibration. No way you'd feel it. Hopefully the sensors would pick it up, but you wouldn't. Now talking to the helicopter people, if your generator, either mechanically, so the rotor in your generator, either mechanically or electrically went out of balance, your helicopter would vibrate seriously. And I've only ever come across it once where electrically, for some reason, the generator went out of balance. And as soon as the pilot switched the generator on, the whole aircraft went. And as soon as he switched it off, the vibration went. And as you all know, those who are on helicopters, you know vibration is our worst enemy. And because it vibrates. So if you ever, the pilot comes on, he says, I switched the generator on and it vibrated badly, that is because your generator is mechanically or electrically out of balance. Just a little hint for you. So let's have a look at how this system works. Okay, let's have a look at how this works. So here's a basic system, okay? There's the heaters on the propeller. That could be the heated windscreen. It doesn't matter. It's a three-phase system, okay? It's a three-phase system. Now, remember I drew the diagram on day one about a three-phase AC system, how we get line voltage and phase voltage, and I talked about the neutral line.
Yes.
Okay. Yep. I remember I also said a neutral line is also a safety device, and it should be able to take the whole load of the generator. Okay. This is where the neutral line comes in. If I have a short circuit, okay, so here's my three phases, okay. There's my neutral line. Yep. As I said, it's 115 volts on each phase. Yep. And again, that neutral line is my datum point, so I can measure from Earth or 0 to the top, which will give me 115. And the neutral line is a safety device that should be able to carry the whole load of my generator, right? So let's look what happens. Oh, who wants to come back in? So let's look at what happens. So normal, okay, normal output of my generator is 115, 115, 115. Yep. And if everything in each of these three phases is correct, what is the potential difference between each of the phases? Anyone? Is it 0 volts?
0.
0 volt, 0 volt. So actually, if it's 0 volts, that means there's nothing on the neutral line. Okay, there's no voltage, no current on the neutral line. Just be aware, gentlemen, this never happens in reality. There is always voltage and current on the neutral line. okay? Enough to kill you. So ideally, there should never, ever be anything on the neutral line. But nothing's ideal. So you always have some current and voltage on the neutral line, and it will be enough to kill you. So never put your finger on the neutral line. Right, so there we go. 0 volts, so they're nothing. This 28 volts is coming from the, okay, sorry. This here, sorry, is my neutral line. I've got 28 volt supply there. And this goes to this relay. And this relay is waiting for a certain amount of voltage or a certain amount of current to cause enough magnetic field to call that contact to come down, that contact to come down to make my warning caption in my cockpit light up. So right now, nothing's happening, okay? Even if one phase slightly drops to 114, the potential difference will not be enough to cause enough current in the neutral line to cause that relay to energize. Let's look now at phase A. Let's say phase A, we now have a short circuit, okay? The cable, the output cable, is chafed against the airframe, okay? I now have an earth leakage or a short circuit. All the current wants to go to earth. So if I have an, what's the ideal voltage left on a phase if I have a short circuit? Ideally, okay, an ideal short circuit will leave me with 0 volts, okay? It might be 3, 4, 5, 6, 7, 8, 9, 10. And in reality, there's always a little bit of voltage, but ideally, it would be 0. Yep. What's the potential difference between 0 and 115? It's 115 volts. So now I have on my neutral line 115 volts. That produces a lot of current. And that goes through the coil of this relay, and now this contact closes, allowing the 28 volts to go to my warning light, and it comes on. Right? It comes on. So there we can see the safety device is a neutral line, but we can use it to actually warn the pilots or a basic light or the ECAM or ECAF system that we have a earth leakage, okay, a earth leakage. But this light or this indication can also come on when we have an undervolts condition. Could I say, is 0 volts an undervolts condition? Well, it's under what we expect. So we could say it is an undervolts condition. But reality is, an earth leakage is a complete short circuit. Let's look at undervolts condition. Okay, we're going to use the same sensing system. Okay, we're going to use the same sensing system. Okay, but we're going to see now how the pilot can tell the difference between an earth leakage or short circuit and or an undervolts condition. So now what I'm going to do, I'm going to draw in. Oh, there's my little. I've lost my arrow. I'm just going to draw something in. Okay, gentlemen, I'm just going to draw something in. I'm going to connect a voltmeter to each one of these phases, okay? Most aircraft have a voltmeter, or those who've got a glass cockpit in the display unit 4 of the ECAM or ECAS system, the lower display, you can actually go and you can get the voltages in each phase. So now what I'm going to say is, let's have a look at the difference between an undervolts condition and a earth leakage condition. We did say 115 volts, 114 volts is slightly low. The system works okay. Let's say now it drops down to 85 volts, okay? What is the potential difference between 85 and 115?
30.
That's 30, yeah, 30 volts. That 30 volts, again, is going to produce a current. And that current is also going to be large enough to energize that coil, close that contact, and put the caption on my earth leakage light or the sensor in the ECAM or ECAS glass cockpit system. So what's the difference between an earth leakage condition and an undervolts condition if it uses the same electrical circuit to give the indication? Well, let's have a look here now. I've got this voltmeter. Okay, so when the pilot gets, and he'll basically probably get a caption saying low A phase or low B phase or low C phase, okay? What the pilot does, he will then look at the voltmeter and he'll look at A phase, B phase and C phase. If he says a voltage that's lower than he expected, i.e. 85 volts or 70 volts, the aircraft, that phase has a undervolts condition because it's under the voltage he expects. He expects to see 115. If he's got 85 or 75 or 65 or 95, it's under what he's expecting. And that's what we mean by an undervolts condition. If he has 0 volts, that's a short circuit, that's a earth leakage, and ideally I would have 0 volts. So what's the difference between an earth leakage and an undervolts condition? An earth leakage would be 0 volts, ideally. An undervolts is under what the pilot would be expecting to see. He's expecting 115. If he's only getting 85 or 90 or 95 or 75, it's under what he's expecting. And how does the pilot know? So how does the pilot know he has the difference between an earth leakage and an undervolts condition? He looks at the voltmeter to determine whether it's a short circuit, earth leakage, or a undervolts condition. Okay, he looks at the earth leakage or undervolts. So he looks at the voltmeter and looks at the system. Well, it looks at the voltmeter. He said, so an undervolts condition is the pilot would go look at the voltmeter to determine if it's a undervolts or earth leakage. Okay, as it says there, earth leakage is very low. And I'm going to say ideally 0 volts. So I can see here, under volts is under what the pilot is expecting. And earth leakage is 0 volts. Okay, and the pilot just looks at the voltmeter and he makes that decision. Okay, so are we all happy now the difference between earth leakage and under volts? Yep. And how does the pilot tell the difference? He just looks at the voltmeter. Okay, he just looks at the voltmeter. Okay, are we all happy on earth leakage and under volts? And are we all happy how we find, or how the pilot would determine the difference? We all happy in that?
Happy.
Good. Can we take a 5-minute break? Okay, I just need to go to the toilet. 5 minutes, we'll come back and we'll hopefully try and finish off soon. Okay, so just a 5-minute break. I'll just go to the toilet and I'll come right back. Okay, gents, that's me back. Right, so the next thing we're going to look at is the next fault, okay? So we've been through the undervolts. Next thing we're going to look at is overvoltage, okay? And overvoltage protection. Now what we're going to look at here, okay? We're going to look at what happens when we get an overvolts condition. And remember we looked at the DC, we had that overvolts latch relay. And when that opened, it moved the generator excitation field. Well, in AC, if we get an overvolts condition, it's going to do the exact same. It's going to remove the generator field. So we can actually say that hasn't changed. How we do it is slightly different, okay? All electronics work with DC, okay? So coming in here, there's my, I've got my 115, okay? And what happens, this is a normal condition, 115, okay? It will change that 115 into a DC value. You don't have to know what it is. It's a DC value that is equal to 115, okay? And we'll just stick with 115 volts, but it's 115 volts DC. This thing here, ZD1, is what's called a Zener diode. Think about it as a pressure relief valve. Voltage is a pressure, okay? And as long as that voltage doesn't go too far above 115, this Zener diode doesn't conduct, okay? And if it doesn't conduct, this transistor T1 doesn't conduct, okay? And what I'm going to get here is, because it doesn't conduct, I'm going to get a voltage here. And that voltage here is going to go onto the base of transistor T2, and it turns that one on. Now what happens is, here's my 115. This transistor T2 is conducting. It's turned on, it's conducting. And look, all my voltage will go, all my voltage will go straight to earth. Nothing goes to this generator field relay, nothing at all. So therefore, my generator works normally. Now let's think what happens if I get to a overvolts condition. My voltage rises. Let's call it 135 volts, okay? That's AC. It would be converted to a value of DC, yeah? And again, we'll call it 135 volts. DC. Now, this Zener diode, okay, the voltage or the pressure, the electrical pressure, is greater enough to cause this Zener diode to open, okay? And if the Zener diode opens, we've now got a flow through the Zener diode to the top of this resistor. And the top of that resistor causes voltage to go to T1. Okay, transistor T1, which now turns on. And now, because it turns on, all this voltage and current goes straight down, past through the transistor to earth. There is now nothing, there's 0 volts on this transistor T2. It turns off. Now let's come up to here. It comes to here, gentlemen. This voltage can't go here. But look, it's got a path to the right. And it goes first to this capacitor. It starts to charge up. This capacitor is therefore little spikes, just like the suppressor in the DC. So any large spikes for a fraction of a second, it'll start to charge up this capacitor. And once the voltage goes back down to 115, it will start to then discharge again back into the system. But if the voltage stays up, this capacitor charges all the way up. And when it's fully charged, that supply now goes to this SCR silicon controlled rectifier. It fires, okay? What we call fires, it opens. And now it's allowed, let's say, a 28 volt supply down through the generator relay coil, causing it to open, removing the generator field. Again, gentlemen, that's no different from DC. And again, gentlemen, the sensor that's going to detect the over voltage is the Zener is a Zener diode. Okay, so the Zener diode, whether it's an AC or DC, is the sensor that will detect the over voltage. And in any over voltage condition, the generator field relay opens, removing the supply to the excitation coil. Okay, you're not going to be asked, because it's very difficult to ask the operation of a circuit in a multiple choice exam, but you have to be able to aware of what happens in an over voltage condition. Well, the sensor that's going to start everything going is the Zener diode. So, and I keep saying to you, gentlemen, it's the exact same for AC or DC. And an overvolts condition is sensed by the Zener diode. What happens in an overvolts condition is the generator field relay opens, removing the excitation voltage. Okay, all happy on what triggers an overvolts condition and what happens when we trigger an overvolts condition. I've got one question for you, gentlemen. What also happens when I move the generator field? I also remove the generator from the bus bar. Okay. Remember I said we remove the generator field, we also remove it from the bus bar by opening up the generator contact breaker. We'll look at that a bit more as well. Okay, we're now going to look at an overload condition. And an overload condition is too much current. Okay. And throughout the aircraft now, we've got things what's called current transformers. They are actually looking, okay, they're looking for excess current flowing in a system. Okay, they're looking for excess current flowing from a system. So, in an overload condition, it's sensed by a current transformer. The system is drawing far too much current. Okay, this could cause damage. So in this situation, we remove the generator field, okay, the generator field, and we must also, if we remove the field, we must also always remove it from the bus bar. Yeah. So in an overload condition, again, we remove the generator from the bus bar. Therefore, how do we do that? We de-excite, we remove the excitation field or the generator field. So that's the overload condition. All happy on that one so far? Good. The next one, something called differential protection. Okay. Again, we're looking at current. What do we know about current in a series circuit? Anyone tell me? What do we know about current in a series circuit?
Same.
It's the exact same, yes. So the current in a series circuit is the same. So in my differential protection circuit, I'm just going to look at one phase, okay? We're going to look at the current coming out of the generator, and we do it by a current transformer. And let's just look at C phase, okay? So let's say out of the current transformer, okay? And this differential protection is from the generator to the generator contact breaker. So we're still on the generating half of my distribution circuit. So let's say I have 100 amps coming out to the generator. That is measured and that goes to the differential protection unit, 100 amps. If this circuit is complete or there is no damage, at this point here, just before I leave the generator side, I will also have 100 amps. And it says there, if the output at X and the output at Y are the same, it is okay. Okay. If they're both the same, it is okay. So let's look at A. Imagine now I chafe away the insulation on that cable. And now that cable touches a frame on the aircraft. Okay, touches the frame of the aircraft. I've got a short circuit, haven't I? Yeah, I've got a short circuit. Or even if the insulation was, it chafed away but was slightly thin, it could still get current to go through. But let's look at a proper short circuit. So now, coming out of my generator, I still have 100 amps. The 100 amps is going to go to the short circuit. And we know, gentlemen, that current always wants to take the shortest path to Earth. So if my cable is chafing or is short-circuiting to one of the frames on the aircraft, ideally I would get 0 amps here. So now I've got 100 amps at this side, 0 amps at that side. The system knows it has a problem. And remember what I said, if I don't do anything, 5 amps can vaporize a frame. So just think what hundreds of amps could do. This system will quickly detect this difference in current at each end of the supply cable. At each end of the supply, it knows it's different. And it will quickly, the first thing it does, it will remove the generator field. Because if X and Y, point X and Y are not equal, it's US. If I remove the generator field, what else do? I must remove the generator from offline by removing or opening the GCB. Yep. So we have to understand that differential protection happens when the current is not the same at both ends of the power supply cable. What happens? The differential protection unit will trip the generator field, and it will, if I remove the generator field, it will also bring the generator offline by opening up the GCB, okay? By opening up the GCB. Are we all happy on that, gentlemen? Are we all happy on what the differential protection? So we need to think about the basic faults we're going to cover. The first one is overheat. Okay, so the first one is overheat. We have the sensor in the exhaust of the generator. Earth leakage. Earth leakage is a short circuit. An undervolts condition is voltage less or voltage under what the pilot was expecting. How does the pilot know the difference between an earth leakage and an undervolts condition? The pilot will look at the voltmeter. In an undervolts condition, what is the sensor, or what detects the overvolts condition? It is the Zener diode. And again, if I have a overvolts condition, I will remove the generator field. And if I remove the generator field, I will take the generator offline by opening up the generator contact breaker. If I have an overload condition, that means I have too much current being drawn from the generator. It is sensed by current transformers. Those current transformers will cause the generator field to be removed, the excitation field to removed. The generator is also taken offline by opening up the generator contact breaker, the GCB. Differential protection. We're looking at the current at both ends of the supply cable coming out of the generator cable. If the current at both ends, again sensed by current transformers, is the same, everything is good. If the current leaving the generator is different from the current just before it goes out to the GCB, something goes wrong. The differential protection circuit will operate, removing the generator field and opening up the GCB, removing the generator from the what was I talking about? From the buzz tiebreaker, okay? From the buzz bar by opening the GCB. One last thing we're going to talk about today, gentlemen. Okay, two last things. On a big aircraft now, okay, think about your big aircraft, 777, your 78, your 787s, your A380s. Think about them as a town, okay? They're a town, a village. All over the aircraft, there is lots of sensors. We've just talked about them, current transformers. There'll be more than one TRU in the aircraft. It'll be looking at certain systems on the aircraft, looking at the power it is producing. It'll also look at the frequency of electricity going to the system. So each generator has its own generator control unit. But we have, and that's the brain for a generator. But we have something called a buzz power control unit, BPCU. That is the big brain of the aircraft power distribution system. It's looking at, it's receiving information from each generator's generator control unit. It doesn't interfere with them. All it knows is if one of them has failed. It's all it's interested if it's failed, and it can look at maybe shutting certain systems down. But the buzz power control unit is also looking at TRUs, current transformers, other electrical systems in the aircraft. So the buzz power control unit is the big brain for the aircraft. Okay, all the electrical systems, the buzz power control unit is looking at those systems, but it's receiving information about what the generator control unit is doing with each generator, but it doesn't control what the GCU does. It only reacts if a GCU says, I'm shutting down my generator. The buzz power control unit can look at maybe taking certain systems, putting certain systems down to keep the load under control. So that's the purpose of the buzz power control unit. We'll now look at the GCU in a bit more. We'll look at it a bit more, what it does. We've talked about it a lot. Now we're going to look at what it does. So the generator control unit, it's two parts, okay? A generator control unit controls its own individual generator. Controls its own individual generator. Yep. But it does several things. The first one is the voltage regulation. Yeah, and we've talked about that all day today. So The first part of a generator control unit is the voltage regulation, keeping the voltage within the correct limits. Next thing is my protection circuits. Now, we've looked at some protection circuits, okay? Probably now on Monday, we'll look at some other protection systems. Okay, we'll look at some other protection. Those circuits we just talked about are common to an AC or DC protection. On Monday, we'll look at protection circuits that are specifically frequency orientated, okay, to do with frequency. Your GCU might have a bite test, okay, to check the electronics is working. Going back to our voltage regulator, what supplies in a brushless AC generator, what normally supplies voltage to the voltage regulator or the GCU? Can anyone tell me? What would supply power to my self-excited brushless AC generator?
PMG.
The PMG. Well done, gentlemen. Well remembered. Normally powered by the PMG. Yep. I'm going to say, gentlemen, that is the way it is normally done. Okay. Though it actually says here, I've actually checked it in the books. It is correct. I've got to say I have never seen a battery powered generator control unit, and I've worked in the workshops working on them, but there you go. So it could be, but gentlemen, all I want you to remember is this. How is my generator control unit normally powered? Oops. Oh, for goodness sake. You get my meaning, okay? So what normally powers my generator control unit is my, we get that, I will determine to get this correct. Yeah. So what normally powers it is the PMG. We've just had a little look at this. Here's a basic one, okay? If you actually look there, there's my generator contactor, okay? My generator breaker, my GCU. If you look here, okay, we're looking for it. If you look at the supply, there's my, it's sampling here my output for my generator, and there is a supply to my excitation. So it's working as normal. If you look in here, here's basically the generator control relay, okay? The generator control relay, which is controlling the field. And if you look here, it's got a close and a trip. Close is supplying. If it trips, it removes the generator from the buzz bar, as it says there, okay? So you can see there's the supply from my PMG to my generator control unit. Okay, so you can now see, if I've now talked about it, what it does. So I've got my PMG rotating, gentlemen. What is going to be induced into the GCU at the first stage? Anyone help me?
AC.
AC, yeah.
AC.
And once the AC, once the AC gets to a set value, what does the GCU provide? Provides excitation in the form of
DC.
Yep.
DC.
Yeah, DC. Yeah, exactly. Well done, gents. And that's going to induce into this rotating exciter generator what type of electricity?
AC.
Yeah, AC. And at this full brave rectifier, it's going to produce a
DC.
DC. And the output of my AC brushless generator is going to be
AC.
AC. And it's going to be what value?
115.
115. Yeah, 400
Hertz.
hertz. Yeah, 400 hertz. So that is going to be what we're going to get out of our generator. Okay, that's what we're going to get out of our generator. Right, one last thing to cover today, gentlemen, and we're going to call it a day. Okay? Hurrah, I hear you say. So, we're looking at, what we're really looking at now is frequency specific faults, okay? So, my GCU is going to look at the faults. It's going to look at the voltage level. It's going to look at the loads, okay, the current, and it's also going to look at the frequency, okay? Remember, our components on our aircraft are designed to operate at 400 hertz, okay? So if the frequency is too high or too low, it's going to cause problems. So we actually need to think about the frequency, and we're going to look at on Monday what we do to check, or what we look at which is going to cause problems with frequency in our generator. Okay, we're going to look at the distribution. Okay, the distribution. How does it do it? Okay, we know how it does it. As long as the GCU knows the generator is rotating at the correct RPM, that means the frequency must be good. As long as my current transformers are saying that the loads leaving the generator and before it goes to the GCU are correct, I can open up my generator control unit and I can connect my generator to my bus bar. Okay. We'll just look at again what the bus power control unit does. Okay, the bus power control unit looks after power management. The whole town. Is the first thing it says. It receives, remember I said that, it receives information from the generator control unit. It doesn't tell it what to do. It monitors any current transformers, yeah, making sure that the current, no differential protection. It monitors the load controller, and it will have load controllers all over the aircraft, especially when I have, let's say, motors, air conditioning plants, anywhere there's going to be a high current. Because if it goes too high, if I've got an electrical motor, if it starts to seize the current, it will try to draw more current. And again, if it still seizes, it will draw a lot of current, it might catch fire. So the air, you don't want to fire at 30,000 feet. So my load controller is monitoring the current going to systems that we know are going to draw a lot of current to start with. And if it sees the current going too high, the bus power control will actually remove the supply from those systems. Okay, so the bus power control unit is not interested in just the generation side, it's how the aircraft is using electricity all over the aircraft. Okay, and it can switch off supply. So if I lose a gen, the GCU goes, okay, I'm shutting my generator down. This can actually determine, do I need to switch things on and off? Do I need to shed loads to keep the load under control? Okay, gentlemen, any questions what we've done today, this afternoon, this morning? We have covered a lot of information. Okay, your brains are probably full. Does anyone want to go through anything we have covered today? Anyone? Now you should have some of the questions in the page. Where we go? The questions again, gentlemen. I do suggest if you get time this weekend, can we have a little look at some of the questions? We're probably up to, yeah, probably about 61. Question 61. Yeah, we're up to about question 61 in these questions. Okay. Ever get any questions? Yes, gentlemen.
Do you have some objective questions as well?
Say that again, please, Chris. Didn't quite hear it.
Objective questions.
Well, they've got the questions in that sheet I've given you already.
Yeah.
Okay.
But with options like 2-3 options and the
No,
right answer.
we're not allowed to give them out, I'm afraid. We can't give multiple choice answers out. The CA and EASA won't allow multiple choice questions to be given out. Much that I would like to give you them, Chris, we're not allowed to give them. And if I was found to give them out, I'd be sacked. Okay? So I'm afraid, sorry, Chris. But these questions here, if you can find them in the book, and also, if you can't find them, the answers are in the back. Okay, so it will help you.
Yeah, but from this electricity, we have level 3 questions, level 3.
Yes. Yeah.
So with the questions you give, can we tackle the level 3 questions?
Yes, you can tackle. Remember, I went through, we talked about some of the faults in the cabin pile regulator. We looked at what is a undervolts and overvolts condition. That is level 3. All the understanding of these, understanding how the system works is level 3. Okay, Chris?
Okay.
Okay. Level 1 is see what it does. Level 3 is understanding. So again, if I was to say to you, Chris, what is the sensor in an overvolts condition? Okay, so you have to know what an overvolts condition is. You have to know what the sensor is, and the sensor is, Chris? Oh, I've stumped you. Evan, help him.
Transformers.
Say it again.
Current transformers.
No.
Genodiode.
It's a Zener diode. Okay. So you have to know what an overall condition, and you have to know what the sensor is. Again, that's a sort of level 3 question. Level 3 questions don't have to be quantum physics.
Is it level 3 in?
Yeah, level C is to have a good understanding. That's what it says, isn't it, right? 1 is basically a statement, 2 is an understanding, level 3 is a good understanding. And knowing what the condition is and knowing what the sensor is a good understanding of a system.
Okay.
Okay. Yep.
Yeah.
So,
Mr. Ian,
anyone want to go through anything we've done today? Yes.
whatever you gave to us, this question is enough for us to study, for exam
Yes,
point of view.
Those questions will get you to read the notes. Okay, combined with what I've been telling you today, you will have enough information.
Okay. But from that question in exam, it will come or not?
I'll hopefully it will. I think it will.
You are the one to make the questions for us?
I don't make all the questions, no. Okay, I don't see the exam paper. Okay, I don't see the exam paper. I'm not allowed to see the exam paper.
Okay.
Okay.
But maybe probably you know the what type of questions it will come, how you will tackle.
If you've been listening to what I've been saying, I've been highlighting a lot of how things work.
Yeah.
Okay. I can't give you the answers because I'll lose my job. But if you've listened to me, what I've been saying,
yes, sir.
Hopefully, that will help you.
Okay.
So do I.
Yeah.
Okay.
Okay.
Okay. Anyone want to go through anything again? Okay. I'm here to go through. If anyone wants to go through it again, I'm here to go through it again. Anyone want to go through anything again? No.
No, I think it's okay.
Not
Yeah.
today.
No, sir.
Not
it's
today.
okay.
Yeah. So go and have a good night's sleep. Okay. I know some of you are working tomorrow, but if you get a chance, read through your notes and read through the questions at the weekend. Okay. And then anything you want, again, if you want to, Yadev's got my email address. If you want to email my works address with any questions, I can have an answer ready for you on Monday morning. Okay.
Okay.
Okay, sir.
Okay.
Okay, sir. Okay, sir.
So
Okay, good night.
good night. If there's nothing, yeah, because good night. Nearly 10 o'clock. 9:30,
Yeah.
10 o'clock. Yeah.
9:30, yeah.
9:30. Okay. You've covered a lot of work today, gentlemen. Okay. And we will finish off on Monday. On Monday, okay, we'll finish off the module 11 part of the course, and then we will do the B2 and the helicopters people for it. So we'll do the direct helicopter bits. It's not too bad. It's just to cover the differences between big helicopters and fixed wing aircraft. Okay, so the Mod 11 people, the fixed wing people, don't need to do the bit we're going to probably do tomorrow and Monday afternoon. Okay, and then on Tuesday we'll do lighting. Okay, so that's the plan for Monday and Tuesday.
Okay, sir.
Okay.
Okay, sir.
Right.
Yeah. Okay.
So if you've got no questions for me, gentlemen, I will see you on Monday. Have a nice weekend.
Okay,
If you
sir.
have any questions,
Okay,
you
sir.
can email me and I'll have the answers for you on Monday morning.
Okay.
Sure, sir.
Sure, yeah.
Okay?
Okay.
Yeah,
Sure,
sure,
sure.
sure.
Okay. Have a nice weekend.
Have a nice night's sleep. Okay? All
Thank
have your
you.
beauty sleep.
You too.
Okay.
Hello, Len.
Yes.
So Model 11 class will over in Monday.
Yes, everyone will be back Monday. And once I've finished this, the Module 11 people can go. And I'm just going to concentrate on the helicopter and the B2s on the course.
Model 11 class will up to on Monday.
Probably about lunchtime, Monday.
Oh, okay, sir. Okay.
Okay, and then I've got to do the helicopter and the B2 specific parts. Okay.
What about the lights, sir? We don't have.
We'll do that Tuesday.
Okay.
Okay, we'll be doing lighting on Tuesday.
Hello, Ian.
Yes.
That chapter 4 is, I think, not required for B1, helicopter power distribution system.
Yes, that's what I said. So the helicopter people and the B2s will be doing the helicopter. The B1s don't have to do the helicopter. Okay, and we'll be doing the helicopter parts on Monday afternoon.
Okay.
Okay. So we'll finish when we finish off. We'll finish off about lunchtime Monday, maybe slightly after, and then I'll do the helicopter parts. And then on Tuesday, everyone back to do the lighting.
Okay, Ian. Thank you.
Okay. Lighting's very easy. Most of the questions in lighting are level 1, and there's only 4 questions in the Module 11 exam anyway. And most of you know everything about lights already, even if you're a mechanical person. Honestly, there's a few extra bits I'll tell you about, but lighting's very easy. Okay, you switch it on, it goes on. If it doesn't, you change the bulb.
Okay, Ian. Good day.
Okay.
In.
Yes, Chris.
Are you there?
I'm here, yes.
Yeah, I have a question.
Yes, please, on you go.
During the installation of a DC generator,
Okay.
The splines are lightly lubricated or thoroughly lubricated.
That would be down to that's a type, that'd be down to your aircraft maintenance manual.
Yeah, but
okay.
Generally when there is spline, so is it any difference between thoroughly lubricated and lightly lubricated on this spline gear?
Again, Chris, I can't be specific because that all would depend on what your aircraft maintenance manual says. Some might say lightly coat, some might be thoroughly coat. That's down to the aircraft maintenance manual. Okay. We're looking at basic how the things work. We're not looking at how you connect them. That is specifically down. Specific requirements like lubrication, that is your aircraft maintenance manual. Okay.
Okay. Yeah.
Okay.
And gasket is installed ever? Have you ever seen in the helicopters? Gasket installed while fitting the generator?
No, all I can say is in my helicopter we didn't fit a gasket. We just put a little bit of a jointing compound to stop the similar metal corrosion. So ours was metal to metal. Yeah. But I know of some aircraft they have got some sort of gasket. Okay. So again, Chris, what I've got to say is these bits, how we connect things up, that's down to the aircraft manufacturer. So therefore that will be in your maintenance manual. Okay. So little things like how we connect things up. Yeah. That's not really covered on this course. Yeah. That's actually covered in your maintenance manual.
I have a question.
Okay.
This is the same. I'm reading in front of you so that you hear. When fitting a typical DC generator to a gearbox, ensure, and the option one is proper gasket is installed and correct torque procedures are used.
Yes.
And the second is the spline gear is thoroughly lubricated with light engine oil.
Okay. Yeah, I completely agree with you, Chris. Okay.
Yeah.
So read what it said about the lubricate. Read exactly what it said again, Chris.
Yeah, a proper gasket is installed and correct procedures are used.
So the correct procedures are used. Where would you find the correct procedures? Would be in the maintenance manual.
Yeah.
So we are saying, as I said there, that example we are given, it said the correct gasket is fitted. Okay.
Yeah.
But what I'm saying is, in my last aircraft, the generator was bolted straight on to the gearbox, but we put, rather than a gasket, we put the old jointing compound to stop the similar metal corrosion. But I did actually say I have seen other helicopters where they put a gasket. So specific gaskets or lubrication, how much you put on is specifically to the aircraft type. You will lubricate it. Yep.
Yeah. So the number one is right then. Correct torque procedures are used. So we will follow the maintenance manual.
Yes, basically, yes.
Okay.
That's what you do. So I'm not going to tell you how to put a generator on your aircraft because I don't know your aircraft.
Yeah.
So you'll always do it by the maintenance manual. Okay. Remember, this is general course of understanding the basics of the aircraft systems. Specific is going to be on your type course.
Yeah, mostly we all have a similar type of helicopter here. We all work in the Airbus helicopter, the Equerel one, B3E. Most of the helicopter operator, we all students work on the same helicopter.
Yeah. Okay.
In Nepal, we have the similar types of helicopter. Every company have the same helicopter.
All right. Okay, that's fine. Okay.
Yeah. Well, as I said, understand now.
Okay. So when we talk about helicopters on Monday, okay, we'll look at, so we've already said you've got your generators on the front of your, is it the front of your, I think it's the front of your gear, it's front, you got the engine there. The gearbox is at the front or the rear of the engine. Yours is at the front, isn't it? The gearbox.
Gearbox is at the front. In the
so you've got the generator connected and your hydraulic pumps are connected at the front. And you've got a DC generator, okay? So we consider your aircraft as small. So what you could actually say about your aircraft is what we talked about, a parallel DC system is specifically really what your aircraft would be. The pure helicopter side is we're looking at the differences and we're talking about the big helicopters, and the difference between them. But some of the requirements of a small helicopter are also covered in the large helicopters, but we have to, even you, because you're going for a 1.3 license, you could be working in a
types of
aircraft you are, and then you might decide I'm going to emigrate to Australia. Okay, and you might be working on the big transport helicopters. So the 1.3 license is covering every helicopter from small to the big, large transport helicopters. Okay.
Okay.
Yeah, so you'll learn some things about big helicopters on Monday.
Thank you.
Okay, right.
Yeah.
Cheers,
I'm
Chris.
leaving now. Okay, enjoy your weekend. Bye.
Bye.